Welcome to the ultimate coding relaxation journey. Get comfortable, settle in, let your body ease into this moment. Let the gentle rhythm of this tutorial start to wash over you. Close your eyes if you like, or simply lean back and breathe. This is a space for learning, but also for calm. As we explore the world of C programming, may the words flow like a lullaby, guiding you through concepts with peace and patience. If you're enjoying the journey, don't forget to like and subscribe for more relaxing coding tutorials. Let the coding begin. This session will provide a comprehensive introduction to the C programming language. We will explore the core principles that make C a foundational language in software development. By the end of this session, you will have a clear understanding of what to expect and why C remains relevant in modern computing. We will begin by outlining the key topics that will be covered, including the history of C, its significance in programming, and the basic structure of a C program. This foundation will set the stage for more advanced concepts in future sessions. The C programming language was created in the 1970s by Dennis Ritchie at Bell Labs. It was designed to provide a flexible and efficient way to write system software, particularly for the development of the Unix operating system. This language was revolutionary because it allowed programmers to write code that was both close to the hardware and highly portable. Over time, C has influenced the creation of many other languages, including C++, Java, and even modern languages like Python and JavaScript, which borrow concepts from C's syntax and structure. Understanding the origins of C helps us appreciate its enduring impact on the field of computer science. Learning C is essential for anyone interested in understanding the inner workings of computers and software. As a low-level language, C gives programmers direct access to memory and hardware, which is crucial for developing efficient and high-performance applications. It is widely used in embedded systems, such as those found in automotive electronics, medical devices, and industrial control systems. Game developers also rely on C for creating fast and responsive applications. Beyond practical applications, studying C enhances your problem-solving skills and deepens your understanding of programming logic, making it easier to learn other languages later. A C program typically begins with the inclusion of header files, which provide access to standard library functions. The line hash includes standard input-output, is used to bring in functions like print, which we use to display output. Every C program must have a main function, which serves as the starting point of execution. Inside the main function, we can use the print function to print messages to the screen. Finally, the program returns a value of 0 to indicate that it has executed successfully. These elements form the basic structure of any C program and are essential for writing functional code. In this section, we will explore the fundamental building blocks of C programming. Variables and data types allow us to store and manipulate different kinds of information, such as integers, floating point numbers, and characters. Constants are values that remain unchanged during program execution and are declared using the const keyword. Operators enable us to perform arithmetic operations, compare values, and combine logical conditions. Control structures like if-else statements and loops let us make decisions and repeat actions, which are vital for creating dynamic and responsive programs. Together, these concepts form the basis of all C programs. Input and output operations are critical for interacting with users and external systems. The scan function allows us to read data from the user, such as integers, characters, or strings, while the print function formats and displays output. For example, we can use scanf to capture a user's name and then use print to greet them. When working with numbers, it is important to ensure that the data types match the format specifiers used in these functions. Understanding how to handle input and output correctly is essential for creating user-friendly and reliable programs. To summarize, C remains a cornerstone of software development due to its efficiency, flexibility, and influence on modern programming. Mastering its syntax and logic requires consistent practice and experimentation. In the next session, we will dive deeper into variables, data types, and operators, building on the foundation established here. By the end of this course, you will have the skills to write efficient and effective C programs. Let us continue exploring the power and versatility of this timeless language. A proper development environment is essential for anyone learning or working with the C programming language. It ensures that coding, compiling, and executing C programs can be done smoothly without interruptions. When the environment is set up correctly, you avoid compatibility issues that might arise due to different operating systems or outdated tools. This setup also enhances productivity by providing access to powerful tools like debuggers, which help identify and fix errors in your code, and code editors that offer features like syntax highlighting and auto-completion. These elements work together to create a seamless workflow, allowing you to focus on writing efficient and error-free code. Choosing the right compiler is a critical step in setting up your development environment. The GNU Compiler Collection, commonly known as GCC, is an open-source compiler that supports multiple platforms, making it a versatile choice for developers. It is widely used in Linux and Mac OS environments and is known for its robustness. Another option is Clang, which is part of the LLVM project. Clang is praised for its fast compilation times and user-friendly error messages, making it an excellent choice for beginners and experienced developers alike. For Windows users, Microsoft Visual C++ or MSVC is a powerful compiler that integrates seamlessly with Visual Studio, providing a comprehensive development environment tailored for Windows applications. Each compiler has its strengths, so selecting the one that best fits your project requirements and operating system is key. Installing the compiler depends on your operating system. On Windows, you can install MinGW, which is a port of GCC for Windows, or use the Microsoft Visual C++ compiler by installing Visual Studio through the Visual Studio installer. For Mac OS users, Homebrew is a convenient package manager that allows you to install GCC by running a simple command like brew install GCC. Alternatively, you can install the Xcode command line tools, which include essential development utilities. On Linux distributions like Debian or Ubuntu, you can use the package manager to install GCC by typing sudo apt install GCC in the terminal. These installation steps ensure that the compiler is available for use, allowing you to compile and run your C programs efficiently. Selecting the right text editor or integrated development environment, or IDE, can significantly impact your coding experience. Visual Studio Code, often referred to as VS Code, is a lightweight and highly customizable code editor that supports C programming through extensions. It offers features like intelligent code completion and debugging tools, making it a popular choice among developers. Code blocks is a user-friendly IDE that comes with built-in support for compilers, making it ideal for those who prefer a more straightforward setup. Eclipse CDT is an advanced IDE tailored for C development, offering a wide range of features for large-scale projects. For users who prefer a minimalistic approach, command-line text editors like Nano or Vim are excellent options for quick edits and lightweight workflows. Each tool has its advantages, so choosing one that aligns with your preferences and project needs is important. Configuring environment variables is a crucial step in ensuring that your compiler and other tools are accessible from the command line. The path variable is a system setting that tells the operating system where to look for executable files. By adding the compiler's installation directory to the path, you can run the compiler from any location in the terminal without specifying the full path. For example, on Linux or Mac OS, you can use the command export path /usr/bin $path to update the path variable. After configuring the path, it's important to verify the installation by running commands like gcc version or clang version. These commands check if the compiler is correctly installed and accessible, ensuring that your development environment is ready for use. Writing and compiling a simple C program is the first step in learning the language. To begin, create a file named helloc and write the following code. #include stdoh, then define the main function. Inside the main function, use the print statement to display hello world followed by a new line. The return 0 statement indicates that the program executed successfully. Once the code is written, compile it using the command gcc helloc. This command tells the compiler to generate an executable file named hello from the source code in helloc. After compilation, run the program by typing hello on Linux or Mac OS, or hello exe on Windows. This process demonstrates how C programs are translated into executable files that can be run on different operating systems. When setting up your development environment, you may encounter common issues that need troubleshooting. If the compiler is not found, it could be due to an incorrect path configuration or an incomplete installation. To resolve this, check the path variable and ensure the compiler's directory is included. Syntax errors, such as missing semicolons or mismatched brackets, are common in C programming and can prevent the code from compiling. Carefully review the code for these issues and use the compiler's error messages to identify the exact location of the problem. Linking errors occur when the program uses functions from external libraries that are not properly linked during compilation. To fix this, ensure that all necessary libraries are included in the compilation command. Addressing these issues systematically helps maintain a smooth development process. In conclusion, a well-configured development environment is the foundation of effective C programming. Familiarizing yourself with the tools and processes involved ensures that you can focus on writing and debugging code without unnecessary obstacles. Whether you choose a compiler like GCC, Clang, or MSVC, or an editor like VS Code or Code Blocks, the key is to understand how these tools work together. Practicing by writing and compiling simple programs builds confidence and reinforces your understanding of the language. As you progress, a solid environment will continue to support your learning and development, enabling you to tackle more complex projects with ease. C syntax defines the set of rules that dictate how to write valid C programs. It includes keywords like if, while, and return, which have specific meanings in the language. Identifiers are names given to variables, functions, and other entities, and they must follow certain naming conventions. Operators such as plus, minus, and equals are used to perform operations on variables and values. Statements are the individual instructions in a program, and each statement must end with a semicolon. It is important to note that C is a case-sensitive language, meaning that my var and my var are considered two different variables. This strictness helps prevent errors, but requires careful attention to detail when writing code. Every C program begins with include directives, which are used to bring in header files that contain function declarations and macro definitions. The main function is the starting point of any C program, and execution begins here. Code blocks are enclosed within curly braces, which help organize and group statements. Comments are essential for documenting code, and they can be written using double forward slashes for single-line comments or asterisks and forward slashes for multi-line comments. These comments are ignored by the compiler, but are invaluable for explaining the purpose of code to other developers. Variables in C are used to store data that can be manipulated throughout a program. For example, an integer variable might hold the value 25, while a character variable could store a single letter. Common data types include integers, floating point numbers, characters, and void for functions that return no value. When naming variables, it is crucial to start with a letter or an underscore, as numbers at the beginning are not allowed. To interact with users, the scanf function is used to read input, and the print function is used to display output. These functions are fundamental for creating dynamic programs that respond to user input. Constants in C are values that do not change during program execution, such as the value of pi in a mathematical calculation. They can be defined using the const keyword or the preprocessor directive define. Literals are the actual values written in the code, such as numeric values like 10 or 3.14, character values like A, or string values like hello. Symbolic constants, whether defined with const or define, make code more readable and easier to maintain. For instance, using pi instead of 3.14 in multiple places ensures consistency and simplifies future updates. C provides a variety of operators to perform different operations. Arithmetic operators like plus, minus, multiplication, and division are used to manipulate numerical values. Relational operators such as equals, not equals, greater than, and less than compare values to determine relationships between them. Logical operators like and, or, and not are used to combine multiple conditions in decision-making. Assignment operators, including equals, plus equals, minus equals, and others, allow for concise updates to variable values. These operators are essential for building complex expressions and control structures. Control structures in C allow programs to make decisions and repeat actions. Conditional statements like if, and else enable the program to execute different code blocks based on specific conditions. Loops such as for, while, and do while let the program repeat a block of code multiple times. The break statement exits a loop or switch case prematurely, while the continue statement skips the current iteration and moves to the next. The go-to statement allows for unconditional jumps to a labeled section of code, though its use is generally discouraged due to potential readability issues. Functions in C are reusable blocks of code that perform specific tasks, such as calculating a result or displaying a message. They help organize code and improve modularity. Variables can have different scopes. Global variables are accessible throughout the entire program, while local variables are confined to the function in which they are declared. The return statement is used to exit a function and pass back a value to the caller. Function prototypes are declarations that inform the compiler about a function's name, parameters, and return type before the function is defined, ensuring proper usage. Mastering C syntax is essential for writing effective and error-free programs. Understanding the structure of a C program, the use of variables and data types, the role of operators, and the flow of control through conditionals and loops forms the foundation of programming in C. Practicing by writing small programs helps reinforce these concepts and build confidence. It is crucial to adhere strictly to C's syntax rules, as even minor mistakes, such as missing semicolons or incorrect capitalization, can lead to compilation errors. Consistent practice and attention to detail are key to becoming proficient in C programming. Variables are like labeled boxes in the computer's memory, where we store information that can change as a program runs. Each variable needs a name to identify it, a data type to specify what kind of data it holds, and a value to represent the actual data. For example, the line int age equals 25 creates a variable called age that stores the number 25. This allows programmers to easily access and modify data throughout the code. In C programming, data types define the kind of data a variable can hold and how much memory it uses. The basic data types include integers, which store whole numbers like 5 or -10, floating point numbers for decimal values like 3.14, characters for single letters or symbols, and doubles for larger decimal numbers. There are also more complex types like arrays, which store multiple values of the same type, pointers that hold memory addresses, and functions, which are blocks of code that perform specific tasks. Users can create their own types using structures, enumerations, and typedefs to organize data more effectively. When we declare a variable, we tell the computer to allocate memory for it. For example, the statement int x reserves space for an integer, but does not assign a value yet. Initialization is the process of giving a variable its first value, such as x equals 10. Combining declaration and initialization, like float price equals 9.99, is a common practice. It is crucial to initialize variables because using them without a value can lead to unpredictable results. A situation known as undefined behavior. The scope of a variable determines where it can be accessed in a program. Local variables exist only within the function. They are declared in and disappear once the function finishes. Global variables, on the other hand, are declared outside all functions and can be accessed from anywhere in the program. Static variables are a special type that retain their value between function calls, making them useful for maintaining state across multiple invocations. Understanding scope helps manage memory and prevent unintended side effects. Constants are values that do not change during program execution, ensuring data integrity. For example, const int max equals 100 defines a constant integer that cannot be modified. Literals are direct values written in the code, such as the number 5, the decimal 3.14, the character A, or the string hello. To define constants, programmers often use the define preprocessor directive or the const keyword. These techniques make code more readable and easier to maintain. Type conversion occurs when data is changed from one type to another. Implicit conversion happens automatically, like when adding an integer and a float, which results in a float. However, explicit casting is required when we want to force a conversion, such as converting a float to an integer. For instance, int 3.14 would result in 3, discarding the decimal part. Proper use of type conversion ensures accurate calculations and avoids data loss. Following best practices for variables improves code quality and readability. Choosing meaningful names, such as student count instead of SC, makes the code easier to understand. Avoiding global variables, unless necessary, reduces the risk of conflicts and makes the program more modular. Limiting the scope of variables to where they are needed helps prevent unintended modifications. Always initializing variables before use ensures predictable behavior and avoids errors caused by uninitialized data. Variables are essential for storing and manipulating data in C programs. Data types determine the size and operations available for each variable, ensuring efficient memory use. Proper declaration, initialization, and managing variable scope are critical for writing reliable code. Constants and type conversion further enhance precision and control, allowing programmers to create robust and maintainable software. By following these principles, developers can build effective solutions in C programming. Constants and literals are fundamental elements in the C programming language that help define fixed values within a program. Literals are values that are directly written into the code, such as numbers, characters, or strings, and they remain unchanged during the execution of the program. Constants, on the other hand, are variables that are declared to hold a fixed value, which cannot be altered once initialized. Both literals and constants play a crucial role in ensuring that programs operate predictably and efficiently. By using fixed values, developers can avoid errors caused by unintended modifications and improve the readability of their code. Understanding the distinction between these two concepts is essential for writing robust and maintainable C programs. Literals are data values that are explicitly written into the source code and are not stored in variables. For example, when you write the number 10 or the string hello in your code, these are literals. They are immutable, meaning their values cannot be changed during the program's execution. This makes them ideal for representing fixed values, such as mathematical constants or specific character codes. Literals can take various forms, including integers, floating point numbers, characters, and strings. Each type of literal has its own syntax and usage, but all serve the purpose of embedding direct values into the code. By using literals, programmers can create clear and concise code that is easier to understand and debug. In C programming, literals are categorized into several types based on their data representation. Integer literals include decimal numbers like 100, hexadecimal values such as 0x1a, and binary numbers like 0b1010. Floating point literals can be written in standard decimal form, such as 3.14, or in scientific notation, like 2.5e3. Character literals are enclosed in single quotes and can represent individual characters, such as A, or escape sequences, like \n for a new line. String literals are enclosed in double quotes and represent sequences of characters, such as C programming. Each of these literal types has specific rules for formatting and usage, and they all contribute to the flexibility and expressiveness of the C language. Constants in C programming are variables that are assigned a fixed value and cannot be modified after their initial assignment. They are typically declared using the const keyword or the define preprocessor directive. For example, const int max equals 100 declares a constant integer that remains unchanged throughout the program. Similarly, define pi 3.14 is a preprocessor macro that replaces all instances of pi with 3.14 during compilation. Constants are essential for maintaining the integrity of values that should not change, such as mathematical constants or configuration parameters. By using constants, programmers can prevent accidental modifications and improve the clarity of their code. The define directive is a preprocessor command used to create macros, which are essentially symbolic constants. When a programmer writes define TAXRAT 0.08, the preprocessor replaces every occurrence of TAXRAT in the code with 0.08 before the program is compiled. This approach is useful for defining constants that are used throughout a program, as it allows for easy modification of a single value. However, it is important to note that define does not provide type safety, meaning the compiler does not check for data types associated with the macro. Additionally, define macros lack scope control, which can lead to potential conflicts if the same macro name is used in different parts of the code. The const keyword in C provides a more modern and type-safe approach to defining constants. When a variable is declared as const, such as const float pi equals 3.14159, the compiler enforces that the value of pi cannot be changed during runtime. This type safety helps prevent accidental modifications and makes the code more reliable. Unlike define macros, const variables have a specific data type, allowing the compiler to perform error checking and optimize memory usage. Additionally, const variables can be scoped to specific functions or blocks of code, reducing the risk of unintended side effects. This makes const a preferred choice for defining constants in modern C programming. When working with constants in C, it is important to follow best practices to ensure code clarity and maintainability. For type-safe and scoped constants, the const keyword is generally preferred over define. However, define can still be useful for macro-like constants, such as define BUFFERSIZ 1024, where the value is used as a replacement rather than a variable. Avoiding magic numbers, unexplained numerical values in code, is crucial for readability, as these can make the code difficult to understand and maintain. Instead, replace magic numbers with named constants that clearly describe their purpose. Additionally, adhering to naming conventions, such as using uppercase letters for define macros, helps distinguish them from regular variables and improves code consistency. In conclusion, constants and literals are essential components of C programming that contribute to the reliability, readability, and maintainability of code. Literals provide direct values within the code, while constants offer a way to define fixed values that cannot be altered during execution. Choosing between define and const depends on the specific requirements of the program, with const being the preferred option for type-safe and scoped constants. By following best practices such as avoiding magic numbers and using meaningful names for constants, programmers can create cleaner and more efficient code. Proper use of these concepts not only enhances the quality of the code, but also makes it easier to debug, modify, and understand over time. Input and output are essential components of any program because they allow communication between the user, the system, and other programs. In the C programming language, these operations are managed through a collection of functions provided by the standard input-output library, known as stdoh. This library contains various functions that enable the program to receive data from external sources, such as the keyboard or files, and to send data to the screen or other devices. The two main categories of input and output are input, which involves receiving data into the program, and output, which involves sending data from the program to an external device. Understanding these concepts is crucial for building interactive and functional programs. The C programming language provides several common functions for handling input and output. The print function is used to display formatted data on the console, allowing developers to present information in a structured way. The scan function is used to read input from the user, typically from the keyboard, and store it in variables. For more specific operations, the getchar function can be used to read a single character at a time, while the putchar function outputs a single character. Additionally, the fgets function is useful for reading strings from input sources, and the fputs function is used to write strings to output devices. These functions form the foundation for handling data flow in C programs. When working with the print and scan functions, it is important to use format specifiers to define the type of data being processed. These specifiers start with a %sign and are followed by a letter that represents the data type. For example, the format specifier %d is used to handle integers. %f is used for floating point numbers. %s is used for strings, and %c is used for single characters. These specifiers ensure that the data is correctly interpreted and displayed, preventing errors that can occur when mismatched data types are used. Proper use of format specifiers is a key skill for any C programmer. In C programming, input and output operations are managed through predefined streams known as standard input, standard output, and standard error. The standard input stream, referred to as STDIN, is typically connected to the keyboard and is used to receive data from the user. The standard output stream, STDOUT, is connected to the console and is used to display data generated by the program. The standard error stream, STDER, is used for outputting error messages and is separate from the standard output to allow for better debugging and logging. These streams are automatically defined in the stdoh library and are essential for managing data flow in programs. To illustrate how input and output functions work in practice, consider a few examples. The print function can be used to display a simple message like "Hello, world" to the console. The scan function can read an integer value from the user and store it in a variable. The getchar function can capture a single character input, such as a letter or symbol, and the putchar function can display a single character on the screen. Additionally, the fgets function is useful for reading an entire line of text, such as a user's name or a sentence, from the input source. These examples demonstrate the versatility of C's input and output functions. Mastering input and output functions is a critical step in learning the C programming language because they enable programs to interact with users and systems. The correct use of format specifiers ensures that data is handled accurately and prevents type-related errors. Always remember to include the stdoh header file at the beginning of your programs to access these functions. Practicing with real-world examples helps reinforce these concepts and builds confidence in writing functional code. By understanding and applying these principles, you can create more dynamic and responsive programs. Operators are symbols that perform operations on variables and values. For example, the plus symbol adds two numbers, and the equal symbol assigns a value to a variable. Expressions are combinations of variables, constants, and operators that evaluate to a single value. Think of an expression as a mathematical formula or a logical condition that results in a specific outcome. Understanding operators and expressions is fundamental for writing logical and efficient C code because they allow you to manipulate data, make decisions, and control program flow. Whether you are performing calculations, comparing values, or creating complex conditions, mastering these concepts is essential for any C programmer. In C programming, there are several types of operators. Arithmetic operators include plus, minus, multiplication, division, and modulus. These are used for basic mathematical operations. Relational operators such as equal to, not equal to, greater than, and less than compare values and return a Boolean result. Logical operators like logical and, logical OR, and logical not are used to combine or invert Boolean conditions. Bitwise operators work on individual bits of integers, allowing for low-level manipulation. Assignment operators like equals, plus equals, and minus equals are used to assign values to variables. Finally, the conditional operator, also known as the ternary operator, provides a concise way to evaluate conditions and return one of two values. Each type of operator serves a unique purpose and contributes to the flexibility of the C language. Arithmetic operators are the foundation of mathematical computations. In C, the plus operator adds two values. The minus operator subtracts one value from another. The multiplication operator multiplies two numbers, and the division operator divides one number by another. The modulus operator returns the remainder after division. For example, if you have an integer variable called result, and you write int result equals 10 plus 5, the result will be 15. These operators are essential for calculations in programs, from simple arithmetic to complex algorithms. Understanding how they work, especially division and modulus, is crucial for avoiding errors in numerical computations. Relational operators compare two values and return a Boolean result, which is either 0 or 1. The equal to operator checks if two values are the same, while the not equal to operator checks if they are different. The greater than operator determines if one value is larger than another, and the less than operator checks if one value is smaller. For instance, in a conditional statement, like if a greater than b, the program evaluates whether the variable a is larger than the variable b. These operators are vital for decision-making in programs, as they allow the code to respond differently based on the relationship between values. Logical operators are used to combine or invert Boolean conditions. The logical AND operator returns true only if both operands are true. The logical OR operator returns true if at least one operand is true. The logical NOT operator inverts the Boolean value of its operand. For example, if you have a condition like x greater than 0 logical AND y less than 10, the program will execute the associated code block only if both conditions are satisfied. These operators are critical for creating complex conditions in control structures like if statements and loops, enabling programs to handle multiple criteria simultaneously. Bitwise operators work on the binary representations of integers, allowing for precise manipulation of individual bits. The bitwise AND operator compares each bit of two numbers and returns 1 if both bits are 1, otherwise 0. The bitwise OR operator returns 1 if at least one of the corresponding bits is 1. The bitwise XOR operator returns 1 if the bits are different. The bitwise NOT operator inverts all the bits of a number. The left shift and right shift operators move the bits of a number to the left or right, effectively multiplying or dividing by powers of 2. For example, if you perform a bitwise AND on the numbers 5 and 3, which are 101 and 11 in binary, the result is 1, which is 1 in decimal. Bitwise operations are commonly used in low-level programming, such as hardware control or optimizing performance. Assignment operators are used to assign values to variables. The simple equals operator assigns a value directly. The plus equals operator adds a value to the variable and then assigns the result. Similarly, the minus equals operator subtracts a value. The multiply equals operator multiplies, and the divide equals operator divides. For instance, the statement x plus equals 5 is equivalent to x equals x x plus 5. These operators make code more concise and readable, reducing the need for repetitive code. They are particularly useful in loops and when updating variable values efficiently. The conditional operator, also known as the ternary operator, provides a compact way to evaluate a condition and return one of two values. The syntax is condition question mark expression 1 colon expression 2. If the condition is true, the operator returns expression 1. Otherwise, it returns expression 2. For example, the statement int max equals a greater than b question mark a colon b assigns the larger of a or b to the variable max. This operator is useful for simplifying if-else statements in situations where a single value needs to be determined based on a condition. However, it should be used judiciously to maintain code clarity. Expressions in C are combinations of variables, constants, and operators that evaluate to a single value. They can be arithmetic, such as a plus be multiplied by c minus d, or logical, such as x greater than 0 logical and y less than 10. Expressions can also be mixed, combining arithmetic and logical operations. For example, a complex expression might involve both calculations and comparisons to determine a result. These expressions are the building blocks of statements in C, allowing programmers to perform calculations, make decisions, and manipulate data dynamically. Understanding how to construct and evaluate expressions is key to writing effective code. Operator precedence determines the order in which operations are performed in an expression. For example, multiplication has higher precedence than addition. So in the expression a plus be multiplied by c, the multiplication occurs first. Parentheses can override this default precedence, ensuring that specific parts of the expression are evaluated first. Associativity defines the order when operators of the same precedence are present. Most operators associate from left to right, meaning that operations are performed sequentially from left to right. For instance, in the expression a plus b plus c, the addition of a and b happens before adding c. Proper use of precedence and associativity is essential for avoiding errors and ensuring that expressions behave as intended. There are several common pitfalls to avoid when working with operators and expressions. One frequent mistake is confusing the assignment operator equals with the equality operator equal to, which can lead to unintended behavior. Ignoring operator precedence can result in expressions evaluating incorrectly. So using parentheses to clarify intent is crucial. Bitwise operations require careful attention to data types, as using the wrong type can produce unexpected bit patterns. Additionally, complex expressions with side effects, such as increment or decrement operators, can lead to undefined behavior if not handled properly. Being aware of these issues helps prevent bugs and ensures code reliability. Operators and expressions are essential for manipulating data in C. They enable programmers to perform calculations, make decisions, and control program flow. Mastering the different types of operators, their precedence, and common mistakes ensures that code is both robust and efficient. Practicing by writing and evaluating expressions helps reinforce understanding and improves problem-solving skills. Whether you are developing simple applications or complex systems, a strong grasp of operators and expressions is a cornerstone of effective C programming. Control structures are the backbone of any programming language. They determine the order in which statements are executed, allowing programs to make decisions and repeat actions. Without control structures, a program would run in a straight line from start to finish, unable to adapt to different situations. In C, these structures include if else, if switch, and loops. Today, we will focus specifically on the if else statement, which is one of the most fundamental tools for implementing decision-making in code. Understanding how to use if else effectively will allow you to create programs that respond dynamically to varying inputs and conditions. The if else statement is designed to handle decision-making scenarios. When a program encounters an if else block, it evaluates a condition. If the condition is true, the code inside the if block runs. If the condition is false, the code inside the else block executes instead. This branching logic is essential for creating programs that can handle multiple possible outcomes. For example, a program might check whether a user's input is valid and then proceed accordingly. By using if else, you can guide the flow of your program based on specific criteria, making your code more flexible and powerful. The basic syntax of an if else statement is straightforward. You start with the keyword if followed by a condition in parentheses. If the condition evaluates to true, code inside the curly braces executes. The else block is optional, but provides an alternative path when the condition is false. It's important to note that conditions in C are evaluated as either true 1 or false 0. While curly braces are required for multiple lines of code, they can be omitted for single-line statements. However, omitting them can lead to confusion, especially when modifying code later. Always use braces to ensure clarity and prevent logical errors. Let's look at an example to see how if else works in practice. Here, we initialize a variable x to 10. The condition checks whether x is greater than 5. If this is true, the program prints x is greater than 5. If not, it prints x is 5 or less. The output depends entirely on the value of x. This simple example demonstrates how if else can control the flow of a program. By changing the value of x, you can observe how the program adapts its behavior. This kind of logic is used in real-world applications, such as validating user input or determining the outcome of a game. Nested if-else statements allow you to handle more complex scenarios by placing one if-else block inside another. For instance, you might first check if a number is greater than another, and then within that block, check a third condition. This creates a hierarchical structure for decision-making. However, nesting can quickly become difficult to read if overused. It's important to balance complexity with clarity. Nested if-else is particularly useful when you need to evaluate multiple interdependent conditions, such as checking user permissions, and then specific role-based access. Always ensure proper indentation to maintain readability. Else if chains provide a cleaner alternative to nested if-else statements. Instead of embedding one if-else inside another, you can chain multiple else if conditions. The program evaluates each condition in order, executing the first block that matches. If none of the conditions are true, the else block runs. This approach reduces the need for deep nesting and improves code readability. For example, you might use an else if chain to check a series of grade thresholds, such as A, B, C, and so on. By structuring your code this way, you can handle multiple scenarios without complicating the logic. When working with if-else statements, there are several common pitfalls to avoid. One frequent mistake is forgetting to use curly braces for multi-line blocks, which can lead to unexpected behavior. Another is confusing the assignment operator equals with the comparison operator equals. which can cause logical errors that are hard to detect. Overlapping conditions in else if chains can also lead to bugs if not carefully managed. For example, if one condition is a subset of another, the order of evaluation matters. Always test edge cases, such as minimum or maximum values, to ensure your code behaves as expected. These practices will help you write robust and reliable code. In conclusion, if-else statements are essential for implementing decision-making in C programs. They allow your code to respond to different conditions, making it more dynamic and interactive. As you progress, you'll find that mastering if-else is the first step toward handling more complex control structures. Practice writing nested and chained if-else statements to build confidence. Remember, the ability to control program flow is a foundational skill that will serve you well in all areas of programming. Keep experimenting with different conditions and scenarios to deepen your understanding. Control structures in C are the fundamental tools that allow programmers to dictate the flow of execution within a program. These structures are divided into two main categories: conditional and iterative mechanisms. Conditional structures, like if statements, make decisions based on certain criteria, while iterative mechanisms, such as loops, enable the repeated execution of a block of code. Understanding these structures is essential for writing efficient and dynamic programs. The key objectives of this section are to explore the three primary loop constructs in C: the for loop, the while loop, and the do while loop. By mastering these, you will gain the ability to automate repetitive tasks and handle complex logic in your code. The for loop is one of the most commonly used iterative structures in C. Its syntax is structured as for initialization, condition, and increment. The initialization step sets the starting value for a loop control variable. The condition determines whether the loop should continue executing, and the increment updates the variable after each iteration. This loop is particularly useful when the number of iterations is known in advance. For example, to print numbers from 1 to 10, you can initialize a variable I to 1. Check if I is less than or equal to 10, and increment I by 1 after each iteration. This structure ensures that the code block runs exactly 10 times, making it ideal for tasks like iterating through arrays or performing calculations over a fixed range. The while loop is another iterative structure in C that executes a block of code repeatedly as long as a specified condition remains true. Unlike the for loop, the while loop does not have an initialization or increment section built into its syntax. Instead, the condition is evaluated before each iteration, which means the loop may not execute at all if the condition is false from the start. A practical example of the while loop is a program that sums numbers entered by the user until they input 0. In this scenario, the loop continues to prompt the user for input and adds the values to a running total until the terminating condition, receiving a 0, is met. This makes the while loop ideal for scenarios where the number of iterations depends on user input or external factors. The do-while loop is unique because it guarantees that the code block inside the loop will execute at least once before the condition is checked. This makes it particularly useful for situations where the loop must run at least once, such as in menu-driven programs. The syntax for the do-while loop begins with the do keyword, followed by the code block, and ends with the while keyword and the condition. For instance, in a menu-driven program, the user is presented with options, and the loop continues to display the menu until they choose to exit. Since the condition is evaluated after the first iteration, the user always sees the menu at least once, even if they immediately decide to terminate the program. Loop control statements in C provide additional flexibility for managing the flow of loops. The break statement allows you to exit a loop prematurely when a specific condition is met. For example, if you are searching for a particular value in an array and find it, you can use break to terminate the loop immediately. The continue statement, on the other hand, skips the remaining code in the current iteration and proceeds to the next iteration of the loop. This is useful for ignoring certain values or conditions without terminating the entire loop. Understanding these statements is crucial for writing efficient and precise code, as they help avoid unnecessary iterations and improve program performance. Nested loops occur when one loop is placed inside another, creating a hierarchical structure of iterations. This is often used to handle multi-dimensional data or perform complex repetitive tasks. For example, a nested for loop can be used to print a multiplication table where the outer loop iterates through the rows and the inner loop iterates through the columns. While nested loops are powerful, they can also be challenging to manage. It is important to avoid excessive nesting, as this can lead to decreased readability and increased complexity. Proper indentation and comments can help clarify the structure, and careful planning is necessary to ensure that the loops behave as intended without causing unintended side effects. When working with loops, there are several common pitfalls to avoid. One of the most frequent issues is infinite loops, which occur when the loop condition never becomes false. This can happen if the increment statement is missing, or if the condition is incorrectly set. Another common error is off by one errors, which arise from using the wrong comparison operator, such as using less than or equal to instead of less than. These mistakes can lead to unexpected behavior, such as missing the last iteration or executing an extra one. To mitigate these issues, it is advisable to use a debugger to step through the code and verify the loop's behavior. Additionally, testing edge cases, such as 0 or maximum values, can help identify and resolve potential problems before they become critical. Loops are a cornerstone of programming in C, enabling the efficient repetition of code blocks to solve a wide range of problems. By mastering the for, while, and do-while loops, you will be able to write more concise and powerful programs. These structures are not just about automation. They are tools for managing complex logic and handling dynamic data. As you practice with examples, you will develop a deeper understanding of how to structure your code for clarity and efficiency. Remember, the key to proficiency lies in consistent practice and experimentation. The more you engage with loops, the more confident and skilled you will become in leveraging their full potential. Arrays are a fundamental data structure in the C programming language that allow you to store multiple elements of the same data type in a single variable. This makes it easier to manage and manipulate groups of related data. For example, instead of declaring individual variables for each number, you can use an array to hold a collection of integers. Arrays provide efficient storage and access because each element can be directly reached using an index, which is a numerical position starting from 0. When declaring an array, you specify the data type, the array name, and the size in square brackets. For instance, the declaration int numbers 5 creates an array that can hold 5 integer values with indices ranging from 0 to 4. This structure is essential for tasks like handling lists, matrices, or any scenario where multiple data items need to be processed together. Accessing elements in an array is done using zero-based indexing, which means the first element is located at index 0. For example, the expression numbers 0 refers to the first element in the array. Each subsequent element is accessed by incrementing the index. It is crucial to remember that valid indices range from 0 up to the size of the array -1. Attempting to access an index outside this range, known as out-of-bounds access, can lead to unpredictable behavior, such as program crashes or data corruption. This is because the memory beyond the array's allocated space may contain other data or be inaccessible. To ensure safe programming practices, always verify that your indices are within the correct bounds when working with arrays. Initializing an array at the time of declaration allows you to set its elements directly. For example, the statement int nums3 1, 2, 3 creates an array with 3 integers, each assigned the specified values. If you provide fewer values than the array size, the remaining elements are automatically initialized to 0, which is particularly useful for static arrays. This behavior helps prevent uninitialized data from causing errors. To determine the number of elements in an array, you can use the expression size of array divided by size of array 0. This technique works because the size of the entire array in bytes is divided by the size of a single element, giving the total count. This method is commonly used in C programming to dynamically calculate the length of an array without hard-coding the value. The size of an array in bytes can be determined using the size of operator, which returns the total memory allocated for the array. For example, if you have an array of integers, the size of the array will be the number of elements multiplied by the size of an integer. To find the size of a single element, you can use the size of operator on a specific element, such as size of array 0, by dividing the total size of the array by the size of one element. You can calculate the number of elements in the array. It is important to note that arrays in C have a fixed size that is determined at compile time, meaning you cannot change the size of an array after it is declared. This characteristic makes arrays suitable for scenarios where the data size is known in advance, but limits their flexibility for dynamic data storage. multidimensional arrays extend the concept of arrays to more than one dimension, allowing you to organize data in a grid-like structure. A two-dimensional array, for instance, can be visualized as a table with rows and columns. The declaration int matrix 34 creates a matrix with 3 rows and 4 columns, where each element is accessed using 2 indices. Similarly, a three-dimensional array, such as int cube 234, represents a structure with depth, rows, and columns. These arrays are stored in memory using row major order, which means that the elements of each row are stored consecutively. This layout is important for understanding how data is accessed and manipulated in memory, especially when working with complex data structures like matrices or 3D models. Accessing elements in a multidimensional array requires multiple indices, each corresponding to a specific dimension. For a two-dimensional array, the expression matrix 12 refers to the third element in the second row. For a three-dimensional array, the expression cube 0, 1, 2 accesses the third element in the second row of the first layer. Iterating through multidimensional arrays typically involves nested loops, where each loop corresponds to a dimension. For example, a pair of nested loops can be used to traverse all elements of a two-dimensional array, while 3 loops are needed for a three-dimensional array. This approach is essential for tasks such as processing images, performing matrix operations, or analyzing data stored in multiple dimensions. Common operations involving arrays include iterating through elements, searching for specific values, sorting the data, and passing arrays to functions. Iteration is often accomplished using for loops, which allow you to process each element in sequence. Searching for elements can be done manually with loops or using built-in functions, depending on the requirements. Sorting algorithms like bubble sort can rearrange the elements in a specific order, such as ascending or descending. When passing arrays to functions, they are treated as pointers, meaning that any modifications made to the array within the function affect the original data. This behavior is useful for functions that need to alter the contents of an array without creating a copy, but it requires careful handling to avoid unintended side effects. Practical applications of arrays include using two-dimensional arrays to represent matrices for mathematical computations, such as solving systems of equations or performing transformations. Three-dimensional arrays can be used to model volumetric data, such as in medical imaging or 3D graphics. Arrays are also essential for storing and manipulating tables of data, such as spreadsheets or databases, where each row and column corresponds to a specific dimension. In image processing, arrays can represent pixel data, with each element storing color information. By leveraging arrays, programmers can efficiently manage complex data structures and perform operations that would otherwise be difficult to implement with individual variables. Arrays are a powerful tool in C programming, offering efficient storage and retrieval of data. They allow you to organize multiple elements of the same type, making it easier to work with large data sets. Multidimensional arrays further extend this capability, enabling the representation of complex data structures like matrices, grids, and 3D models. Mastering concepts such as indexing, initialization, and memory management is crucial for effective array usage. Practicing with real-world examples, such as implementing sorting algorithms or processing images, can deepen your understanding and improve your ability to solve programming challenges. By applying these principles, you can harness the full potential of arrays in your C programs. Pointers are variables that store memory addresses. Unlike regular variables that hold values, pointers hold the location of where data is stored in memory. This allows programmers to directly manipulate memory, which is a powerful feature in the C programming language. The two key operators used with pointers are the addressive operator and the dereference operator. The addressive operator, which is a hash symbol, retrieves the memory address of a variable, while the dereference operator, which is an asterisk, accesses the value stored at that address. Pointers are essential for tasks such as dynamic memory allocation, where memory is allocated at runtime, and for handling data structures efficiently. They provide a way to work with data at a low level, which is crucial for system-level programming and optimizing performance. Every variable in C occupies a specific memory location, which can be identified by a unique address. These addresses are typically represented in hexadecimal format, such as 0x7 FV3B 8A9 F8. Hexadecimal is used because it provides a compact way to represent large numbers, which are common in memory addresses. Pointers enable programmers to access and modify these memory locations directly, which is vital for tasks like reading from or writing to specific parts of memory. Understanding how memory is laid out, including concepts like stack and heap, is critical for low-level programming. This knowledge helps in debugging issues related to memory corruption and ensures efficient use of system resources. Declaring a pointer in C requires specifying the data type it will point to, followed by an asterisk and the pointer name. For example, the declaration int ptr indicates that ptr is a pointer to an integer. This syntax is different from regular variables, where the asterisk is part of the pointer's type, not the variable name. To assign an address to a pointer, the addressive operator is used. For instance, if there is a variable named x, the pointer ptr can be assigned the address of x by writing ptr equals, and x, once a pointer holds a valid address, the dereference operator is used to access the value stored at that location, allowing modifications to the original variable through the pointer. Dereferencing a pointer means accessing the value stored at the memory address it points to. For example, if an integer variable x is assigned the value 10, a pointer to x can be created and used to print the value of x by dereferencing the pointer. However, it is crucial to ensure that the pointer is valid before dereferencing it. Dereferencing a null pointer or an uninitialized pointer can lead to undefined behavior, such as program crashes or data corruption. Pointers are particularly useful in functions where changes to variables need to be reflected outside the function's scope, as they allow direct modification of the original data. This makes them a fundamental tool for passing data by reference. Pointer arithmetic involves performing operations like incrementing or decrementing a pointer to navigate through memory. The result of these operations depends on the data type the pointer is pointing to. For example, incrementing an integer pointer by 1 moves the address by the size of an integer, typically 4 bytes. This feature is especially useful for traversing arrays and dynamically allocated memory blocks. However, pointer arithmetic must be handled carefully. Subtracting 2 pointers that do not point to elements within the same array can lead to undefined behavior. Proper use of pointer arithmetic allows for efficient iteration and manipulation of data structures, making it a powerful aspect of C programming. In C, array names behave like pointers in most contexts, meaning can be used to access elements of the array. For instance, the expression array is equivalent to R plus I, where R is the base address of the array. This relationship allows pointers to be used for dynamic array manipulation, such as resizing or reordering elements. Passing arrays to functions using pointers is more efficient than copying the entire array, as it reduces memory usage and improves performance. Pointers also enable the creation of flexible data structures, such as linked lists and trees, which are essential for complex algorithms and data management. Using pointers as function parameters allows functions to modify the original variables passed to them, which is known as pass by reference. For example, a function that increments a variable can take a pointer to that variable and update its value directly. This is achieved by dereferencing the pointer within the function. However, care must be taken to avoid aliasing, where multiple pointers reference the same memory location, leading to unintended side effects. Pointers are commonly used in functions that need to return multiple values or modify data in place, making them a versatile tool for building modular and efficient code. One of the most common pitfalls when working with pointers is creating dangling pointers, which occur when a pointer references memory that has already been freed. This can lead to unpredictable behavior when the pointer is dereferenced. Another critical issue is null pointer dereference, where a pointer that is not initialized or set to null is used to access memory, resulting in a program crash. Memory leaks are another concern, as they occur when dynamically allocated memory is not properly freed, leading to wasted resources. Additionally, misuse of pointer arithmetic, such as adding or subtracting pointers that do not belong to the same array, can cause errors. Understanding these pitfalls and practicing safe pointer usage is essential for writing reliable C programs. Pointers are a fundamental concept in the C programming language, forming the basis for memory management and efficient data handling. By mastering the use of addresses and pointers, programmers can create optimized and flexible code that interacts directly with system resources. This skill is crucial for developing applications that require high performance, such as operating systems, device drivers, and embedded systems. While pointers offer great power, they also require careful handling to avoid common errors. Through practice and a deep understanding of their mechanics, students can unlock the full potential of C programming and advance their skills in system-level development. Strings in C are arrays of characters that end with a null terminator, which is a special character represented as \0. This null terminator is essential because it tells functions like strlen or print where the string ends. Character arrays are used to store sequences of characters, making them ideal for tasks like handling text input, processing user data, or manipulating strings in programs. Understanding how strings work is crucial because improper handling can lead to errors like buffer overflows or undefined behavior. For example, if you forget to include the null terminator, functions that rely on it might read beyond the array, causing crashes or security vulnerabilities. To declare a character array in C, you specify the size of the array. For instance, char str10 creates an array that can hold up to 10 characters. But remember that the last position must be reserved for the null terminator. When initializing a string, you can use char str equals hello, which automatically calculates the required size, including the null terminator. This is different from declaring a fixed array without initialization, where you must manually ensure the size is sufficient. The null terminator is always added at the end of the string, even if you don't see it in the code. String literals are sequences of characters enclosed in double quotes, such as hello world. These literals are stored in a read-only section of memory, meaning you cannot modify their contents after they are defined. For example, if you write char str C programming, the pointer str points to a memory location that cannot be changed. Attempting to alter the characters in this string, like str0 equals a, will result in undefined behavior. This is why string literals are often used for constant data and not for modifying text during program execution. The null character, which is represented as \0, is a critical component of strings in C. It marks the end of the string, allowing functions to determine where the string stops. Without this null terminator, functions like strlen might continue reading memory beyond the intended string, leading to incorrect results or program crashes. For example, if you have a character array that is not properly null terminated, the function could read into adjacent memory locations, which might contain unrelated data. Always ensure that your arrays are large enough to hold both the characters and the null terminator. There are several common string functions in C that are used for manipulating strings. The strlen function returns the length of a string by counting the characters until it encounters the null terminator. The strcpy function copies the contents of one string to another, but you must ensure the destination array is large enough to avoid overflow. The strcat function appends one string to another, which is useful for concatenation. The strcmp function compares two strings lexicographically, returning a negative value if the first string is less than the second, 0 if they are equal, and a positive value if the first is greater. These functions are fundamental for string operations, but require careful handling to prevent errors. When working with input and output for strings, functions like scanf, fgets, and print are commonly used. The scanf function with the %s format specifier reads a string from input, but it stops at the first whitespace character, making it unsuitable for input with spaces. The fgets function is safer because it reads a line of text, including spaces, up to a specified size, which helps prevent buffer overflows. The print function uses the %s format specifier to print a string, and it relies on the null terminator to know when to stop. Always use fgets for safer input, and be mindful of buffer sizes when handling user-provided data. Buffer overflow is a significant risk when working with character arrays in C. If you write more data into an array than it can hold, it can overwrite adjacent memory, leading to unpredictable behavior, crashes, or security vulnerabilities. For example, using strcpy without checking the destination size can result in a buffer overflow. To mitigate this, use functions like strncpy, which allows you to specify the maximum number of characters to copy, or snprint, which is useful for formatted output. Always validate input sizes before storing them in arrays, and consider using safer alternatives like fgets for input. These practices help protect your program from common exploits and ensure robust code. Following best practices when working with strings and character arrays can prevent many common issues. Always initialize arrays with a sufficient size to accommodate the expected data and the null terminator. For input, prefer fgets over scanf to handle spaces and avoid buffer overflows. Avoid modifying string literals, as they are stored in read-only memory, and attempting to change them can cause crashes. When writing custom string functions, ensure that the null terminator is properly handled to maintain string integrity. These habits promote safer, more reliable code and reduce the likelihood of runtime errors. In summary, strings and character arrays are essential for text handling in C programming. They provide the foundation for tasks like input processing, data manipulation, and output generation. Proper use of null terminators ensures that string functions operate correctly and safely. Prioritizing input validation and buffer management helps prevent errors and enhances the security of your programs. By following best practices and understanding the underlying mechanics, you can effectively leverage strings to build robust and efficient C applications. Structures in C are a powerful way to group variables of different data types under a single name. This allows you to create complex data types that can represent real-world entities more effectively. For example, a student record might include a name, age, and grade, all stored within a single structure. The syntax for a structure is straightforward. You start with the keyword struct, followed by a list of members enclosed in curly braces. Each member has a data type and a name. Finally, you can declare a variable of this structure type. This organization makes it easier to manage related data as a single unit. To define a structure, you first specify its members with their respective data types. For instance, a structure called student might have a character array for the name, an integer for the age, and a float for the GPA. Once the structure is defined, you can initialize it by assigning values to each member in the order they appear. This initialization is done using the same curly braces as the structure definition. For example, struct student S1 equals John 23.7 creates a variable S1 with the specified values. This method ensures that all members are set up correctly when the structure is created. Accessing members of a structure is done using the dot operator, which is a period symbol. For example, S1 age equals 21 modifies the age member of the structure, S1. This operator allows you to read from or write to individual members of the structure. When working with pointers to structures, you use the arrow operator, which is a hyphen followed by a greater than sign. If you have a pointer to a structure, you can access its members using the arrow operator. This flexibility is essential for manipulating data stored in structures efficiently. Unions in C are similar to structures, but with a key difference. While structures allocate separate memory for each member, unions share the same memory location for all their members. This means only one member of a union can hold a value at any given time. Unions are defined using the keyword union, followed by the members in curly braces. The syntax is similar to structures, but with the union keyword. This feature makes unions useful when you need to store different data types in the same memory space. But you only need to use one at a time. Accessing members of a union is done in the same way as structures, using the dot operator. For example, if you have a union called data with members I and F, you can assign a value to one of them, such as D1 value equals 10. However, because all members share the same memory, the value of one member can overwrite the others. This requires careful handling to avoid unexpected results. The example provided illustrates a union with an integer and a float, showing how the same memory location can be used for different data types. The size of a union is determined by the largest member it contains. This is because all members share the same memory space, and the union must be large enough to hold the largest possible value. For instance, a union with an integer and a float would have a size equal to the size of the float, which is typically 4 bytes. This feature makes unions efficient for memory optimization, as they avoid allocating separate space for each member. However, it also means that the data stored in a union can be overwritten if not managed carefully. Structures and unions serve different purposes in C programming. Structures allocate separate memory for each member, allowing all members to hold values simultaneously. This makes them ideal for grouping related data, such as a student's name, age, and grade. Unions, on the other hand, share the same memory space for all members, meaning only one member can hold a value at a time. This makes unions useful for memory efficiency when only one data type is needed at a time. Choosing between the two depends on the specific requirements of your program. Structures are commonly used to represent real-world entities with multiple attributes. For example, a car structure might include the make, model, and year of the vehicle. This allows you to handle all related data as a single unit, making your code more organized and easier to manage. Unions, meanwhile, are useful for scenarios where a variable can take on different types. For instance, a sensor reading might be an integer or a float, depending on the situation. Using a union allows you to store either type in the same memory space, optimizing resource usage. One common pitfall when using structures is forgetting to initialize all members, which can lead to undefined behavior. For example, if a structure has a character array and an integer, leaving the array uninitialized might result in garbage values. With unions, accessing the wrong member can also cause issues, as the data stored in one member may be overwritten by another. Additionally, using unions for unrelated data types can lead to data corruption, as the shared memory space may not be suitable for the intended operations. It is crucial to understand the limitations and proper usage of both structures and unions to avoid these problems. In conclusion, structures and unions are essential tools for organizing and managing complex data in C programs. Structures allow you to group related data into a single unit, making your code more readable and maintainable. Unions, on the other hand, help optimize memory usage by allowing different data types to share the same memory space. Mastering these concepts enables you to handle data more efficiently, leading to better designed programs. Whether you're representing real-world entities or managing variable data types, understanding structures and unions is key to writing effective C code. File handling in the C programming language allows developers to read data from and write data to files stored on a computer's storage system. This capability is essential for tasks such as saving user preferences, logging application activity, or processing large data sets that cannot fit entirely in memory. By using file handling, programs can retain information between executions, which is known as data persistence. The C standard library provides several functions for this purpose, including fopen to open a file, fclose to close it, and freed and fwrite to transfer data. Files can exist in two primary formats: text-based, which stores human-readable characters, or binary, which stores data in a compact, machine-specific format. Understanding these concepts is fundamental for building robust applications that interact with external data sources. When working with files in C, the mode parameter determines how the file is accessed. The The mode R opens a file for reading, but the file must already exist, otherwise the operation fails. The mode W creates a new file or overwrites an existing one, making it suitable for writing new data. The A mode appends data to the end of a file, preserving its existing contents. For scenarios requiring both reading and writing, modes like R open a file for modification, but the file must exist. The W+ mode creates a new file or overwrites an existing one, allowing both read and write operations. Finally, A+ enables reading and appending, ensuring new data is added without erasing the file's current content. Choosing the correct mode is critical to avoid unintended data loss or access violations. The fopen function is the gateway to file operations in C. It requires two arguments: the file name, which is a string specifying the file's location, and the mode, which dictates how the file is accessed. The function returns a file pointer, a data type used to reference the file in subsequent operations. If the file cannot be opened, fopen returns a null pointer, a condition that must be checked immediately to prevent program crashes. The fclose function is equally important, as it closes the file and releases system resources. It takes a file pointer as input and returns 0 on success, signaling that the file has been properly closed. Always verifying the success of these operations ensures that files are managed safely and efficiently. Reading data from files in C can be accomplished using functions like fscanf, fgets, and freed. The fscanf function is ideal for parsing formatted input, such as reading integers, strings, or floating point numbers from a text file. For example, it can extract data from a log file line by line. The fgets function reads a line of text from a file, making it a safer alternative to scanf for handling user input or text data. For binary files, which store data in a non-human readable format, the freed function is used to transfer blocks of data into memory. Detecting the end of a file is crucial, and the fief function can be used to check if the end has been reached. However, relying solely on fief may not always be sufficient, so combining it with return values of read operations ensures accurate results. Writing data to files in C is achieved through functions such as fprint, fputs, and fwrite. The fprint function operates similarly to the print function, but directs output to a file making it suitable for generating reports or storing structured data. The fputs function writes a string to a file, which is useful for logging messages or saving text content. For binary files, the fwrite function is employed to write raw data in its original format, preserving the integrity of complex data structures. It is essential to open the file in the correct mode, such as W for writing or A for appending, to ensure that the data is written appropriately. Neglecting to use the right mode can lead to overwriting existing data or failing to create new files. So careful attention to this detail is vital. File pointers in C allow programs to navigate within a file, enabling operations like random access or modifying specific sections. The fseek function moves the file pointer to a designated position using an offset and an origin. The origin can be set to seekset to start from the beginning, seekcur to move relative to the current position, or seeknd to start from the end of the file. The ftel function returns the current position of the file pointer, which is useful for tracking where the next read or write operation will occur. The rewind function resets the file pointer to the beginning, simplifying tasks like rereading a file's contents. These functions provide flexibility, allowing developers to process files in nonlinear ways, such as skipping sections or updating specific data. Error handling is a cornerstone of reliable file operations in C after calling functions like fopen, freed, or fwrite. It is crucial to check their return values. For instance, if fopen returns a null pointer, the program must handle the failure gracefully, perhaps by displaying an error message or exiting. The parer function can be used to print descriptive error messages, while farer checks for any errors that may have occurred during file operations. Even after successful operations, it is important to verify that the data was written or read correctly. Finally, always closing files after use ensures that all buffered data is properly saved and system resources are freed, preventing potential data corruption or resource leaks. Adhering to best practices in file handling enhances the reliability and security of C programs. Always closing files after use is non-negotiable, as it ensures data is flushed and resources are released. Validating file operations, such as checking if fopen returns a null pointer, prevents crashes and unexpected behavior. When dealing with non-text data, such as images or serialized objects. Using binary mode is essential to avoid issues with character encoding or line endings. Hard-coding file paths can make programs inflexible, so using variables or user input for file names is preferable. Additionally, using fgets instead of scanf for input reduces the risk of buffer overflows, making the program more secure. These practices collectively contribute to robust and maintainable code. To illustrate file handling in action, consider a simple example. First, open a file for writing using the fopen function with the W mode. If the file does not exist, it will be created. Otherwise, its contents will be overwritten. Next, use the fprint function to write a string like hello world into the file. After writing, always close the file with fclose to ensure the data is saved. Later, to read the data, open the file again, this time using the R mode. Then use fscanf to read the string into a buffer. However, it is critical to include error checks after each step, such as verifying that the file pointer is not null. This example demonstrates the basic workflow of reading and writing, but real-world applications often involve more complex operations, such as handling multiple files or processing large datasets. In summary, file handling in C is a powerful tool for storing and retrieving data, enabling programs to interact with external storage systems. Mastering functions like fopen, fclose, freed, fwrite, and fseek is essential for building applications that manage data effectively. Prioritizing error checking and resource cleanup ensures that programs are resilient to failures and maintain data integrity. By following best practices such as validating operations, using appropriate file modes, and avoiding hard-coded paths, developers can create robust and secure file handling routines. These principles are fundamental to writing efficient and reliable C programs that meet real-world requirements. Preprocessor directives are instructions that the compiler processes before executing the actual code. These directives are not part of the C language itself, but are part of the preprocessing phase, which occurs before compilation. They start with a hash symbol, which is often referred to as a hash. The primary purpose of these directives is to modify the code, enable conditional compilation, and define macros. For example, they can be used to include header files, define constants, or control which parts of the code are compiled based on specific conditions. Understanding these directives is crucial for writing efficient and maintainable C programs. The purpose of preprocessor directives is multifaceted. One key use is conditional compilation, which allows developers to include or exclude sections of code based on certain conditions. This is particularly useful for debugging or supporting multiple platforms. Another purpose is defining macros, which can act as placeholders for constants or code snippets, making the code more readable and easier to modify. Including header files is another essential function, as it allows the reuse of code from other files or standard libraries. Additionally, directives like pragma once help prevent multiple inclusions of the same file, which can cause errors. Overall, these directives enhance code maintainability, portability, and flexibility, making them indispensable in complex projects. Common preprocessor directives include define, include, ifdef, ifndef, else, ndif, undef, and pragma. The define directive is used to create macros or constants, such as defining a value for pi. The include directive is used to bring in external files, like header files, which contain function declarations or other code. The ifdef and ifndef directives check whether a macro has been defined, allowing for conditional compilation. The else and ndif directives work in conjunction with ifdef to create blocks of code that are compiled under specific conditions. The undef directive removes a previously defined macro, which can be useful for resetting configurations. Lastly, the pragma directive provides compiler-specific instructions, such as ensuring a header file is included only once. These directives form the backbone of many C programming practices. Examples of preprocessor usage illustrate their practical applications. For instance, defining a constant like pi using define pi 3.14159 allows the value to be reused throughout the code, making updates easier. Including standard libraries, such as include stdoh, provides access to functions like printf and scanf. Conditional compilation, such as ifdef debug, enables developers to include debugging code only when necessary. Macros like define squarks xx allow for inline calculations, though care must be taken to avoid unintended side effects. Finally, using ifndef headrah ensures that a header file is not included multiple times, which can prevent compilation errors. These examples highlight how preprocessor directives streamline development and improve code efficiency. The benefits of preprocessor directives are numerous. They simplify code maintenance by allowing developers to replace repetitive code with macros, reducing the risk of errors. They also enable platform-specific code compilation, which is vital for cross-platform applications. By reusing code snippets through macros, developers can minimize redundancy and improve readability. Symbolic constants, such as pi, make the code more understandable and easier to modify. Additionally, conditional blocks like ifdef debug facilitate debugging and testing. By allowing specific sections of code to be activated or deactivated as needed. These advantages make preprocessor directives a powerful tool in a programmer's arsenal. Best practices and pitfalls associated with preprocessor directives require careful consideration. Complex macros can lead to unexpected behavior, so it is often better to use inline functions for safety. Header files should always include if and def guards to prevent duplicate inclusions, which can cause compilation issues. Macros should be kept simple, well documented, and consistent to avoid confusion. Excessive use of ifdef can make code harder to read, so it is advisable to use them judiciously. Testing code under different preprocessor configurations ensures that all possible scenarios are accounted for. By following these guidelines, developers can harness the power of preprocessor directives while minimizing potential drawbacks. Preprocessor directives are an essential component of C programming, offering flexibility, maintainability, and portability. They allow developers to adapt code to different environments, streamline repetitive tasks, and manage complex projects efficiently. However, their proper usage requires a deep understanding of their capabilities and limitations. Following best practices ensures that these directives enhance rather than complicate the code. Mastery of preprocessor techniques not only improves code efficiency, but also empowers programmers to tackle more advanced challenges in C development. With careful application, these directives remain a cornerstone of effective software engineering. Dynamic memory allocation is a powerful feature in the C programming language that allows programs to request memory at runtime rather than at compile time. This flexibility is crucial because it enables programs to adapt to varying data requirements as they execute. Unlike stack memory, which is automatically managed by the compiler and has a fixed size, dynamic memory allocation uses the heap. The heap is a larger, more flexible region of memory that programmers must manage manually. This approach is essential for creating complex data structures like linked lists, trees, and graphs, which require memory to be allocated and deallocated dynamically as the program runs. The C language provides several functions to handle this process, including malloc, calloc, realloc, and free. These functions give developers precise control over memory usage, but they also demand careful handling to avoid common errors. To understand dynamic memory allocation, it is important to distinguish between two key memory regions, the heap and the stack. The stack is a region of memory that is automatically managed by the compiler. It is used for local variables and function calls, and its size is typically limited by the system. In contrast, the heap is a manually managed area of memory that allows for greater flexibility. Programmers must explicitly allocate and release memory on the heap, which can lead to challenges if not handled properly. One such challenge is memory leaks, which occur when allocated memory is not properly released. This can cause a program to consume increasing amounts of memory over time, eventually leading to performance issues or crashes. Another issue is fragmentation, which happens when memory is allocated and freed in a way that leaves small, unusable gaps. These gaps can reduce the efficiency of memory usage and make it difficult to allocate larger blocks of memory. The malloc function is one of the primary tools for dynamic memory allocation. In C, its syntax is void pointer malloc size t size. This means that malloc takes a single argument, which is the number of bytes to allocate, and returns a void pointer to the beginning of the allocated memory block. It is important to note that the returned pointer must be cast to the appropriate data type before use. For example, if you want to allocate memory for an array of integers, you would use a cast to an integer pointer. A typical example is int array equals cast int pointer malloc 10 times size of int. This line of code allocates enough memory for 10 integers and assigns the address to the array pointer. However, it is crucial to remember that malloc does not initialize the allocated memory. The contents of the allocated block are undefined until explicitly set by the programmer. The calloc function is another essential tool for dynamic memory allocation. Its syntax is void pointer calloc, size t, number size t size. Unlike malloc, which allocates memory without initializing it, calloc initializes all bits of the allocated memory to 0. This makes it particularly useful for allocating arrays of objects, as it ensures that the memory starts in a known state. For instance, if you need an array of 10 integers, you can use calloc to allocate the memory and automatically set each element to 0. This is especially important in scenarios where uninitialized data could lead to unpredictable behavior. The example int array equals cast int pointer calloc 10 size of int demonstrates how calloc simplifies the process of creating arrays with 0 initialized values. While calloc may be slightly slower than malloc due to the initialization step, it is often worth the trade-off for safety and reliability. The realloc function provides a way to resize a previously allocated memory block. Its syntax is void pointer realloc void pointer pointer size t new size. This function is useful when the size of a data structure needs to change during program execution. For example, if an array needs to grow beyond its initial allocation, realloc can be used to expand it. The function may either extend the existing block of memory or move it to a new location if the original block is too small. It is important to note that the pointer returned by realloc may be different from the original pointer, so the programmer must always assign the result back to the original pointer variable. An example of this is r equals cast int pointer realloc r 20 times size of int. This line of code resizes the array to hold 20 integers, ensuring that the program can handle larger data sets without needing to manually copy data to a new block. The free function is used to release memory that was previously allocated by malloc, calloc, or realloc. Its syntax is void free void pointer pointer. When a program calls free, it informs the system that the specified memory block is no longer needed and can be reused. This is a critical step in managing dynamic memory, as failing to free allocated memory can lead to memory leaks. However, it is equally important to ensure that the pointer passed to free is valid and has not already been freed. Using an invalid pointer or attempting to free memory that was not dynamically allocated can cause undefined behavior, including program crashes. Once memory is freed, the program should not attempt to access it, as the contents may be overwritten or corrupted. Proper use of free is essential for maintaining the efficiency and stability of a program. When working with dynamic memory in C, there are several common pitfalls that programmers must be aware of. One of the most frequent issues is forgetting to free allocated memory, which leads to memory leaks. Over time, these leaks can consume significant amounts of memory, causing the program to slow down or crash. Another critical problem is accessing memory after it has been freed, which results in dangling pointers. These pointers point to memory that is no longer reserved for the program, leading to unpredictable behavior. Allocating too much memory at once can also be problematic, as it may exhaust the available heap space and prevent the program from functioning correctly. Finally, failing to check the return value of memory allocation functions like malloc or calloc can lead to crashes if the allocation fails, since these functions return a null pointer when memory is unavailable. It is essential to handle this case explicitly in the code to avoid the common pitfalls of dynamic memory allocation. It is important to follow best practices that promote safe and efficient memory management. First and foremost, always check the return value of memory allocation functions. If the function returns a null pointer, the program should handle this error gracefully instead of assuming the allocation succeeded. Second, release memory as soon as it is no longer needed. This helps prevent memory leaks and ensures that the heap remains available for other parts of the program. Third, use calloc instead of malloc when initializing arrays, as it guarantees that the memory is zeroed out, reducing the risk of undefined behavior. Finally, avoid fragmentation by allocating memory in large, contiguous blocks whenever possible. Fragmentation can make it difficult to find suitable memory regions for future allocations. So planning memory usage carefully can improve overall performance. Dynamic memory allocation plays a vital role in many real-world applications, particularly in scenarios where memory requirements are not known in advance. For example, dynamic data structures like stacks, queues, and graphs rely on the ability to allocate and deallocate memory as elements are added or removed. This flexibility is also essential for handling variable-sized input, such as when reading data from a file or a network stream. in resource-constrained systems, such as embedded devices or mobile applications, efficient memory management is critical to ensure optimal performance. Programmers often implement custom memory managers to control how memory is allocated and reused, which can lead to significant improvements in speed and reliability. By mastering dynamic memory allocation, developers can create more scalable and adaptable software that meets the demands of complex real-world problems. Dynamic memory allocation is a fundamental concept in C programming that provides the flexibility needed to build complex and efficient applications. By understanding how functions like malloc, calloc, realloc, and free work, programmers can manage memory effectively and avoid common errors. It is crucial to prioritize proper memory management techniques, such as checking for allocation failures, releasing memory when it is no longer needed, and avoiding practices that lead to leaks or fragmentation. As with any powerful tool, dynamic memory allocation requires careful handling to ensure that programs run smoothly and efficiently. Practicing with real-world examples and experimenting with different allocation strategies will help reinforce these concepts and improve overall proficiency. With dedication and attention to detail, developers can harness the full potential of dynamic memory allocation to create robust and reliable software. Function pointers are a powerful feature in the C programming language that allow you to store the address of a function in a variable. This means that instead of directly calling a function, you can use a pointer to refer to it. This capability enables dynamic function calls, where the specific function to be executed is determined at runtime rather than being hard-coded. For example, imagine a program that needs to perform different operations based on user input or system conditions. Function pointers make it possible to select the appropriate function dynamically. They are widely used in scenarios like implementing callback mechanisms, where one function can trigger another function's execution, and in creating function-level abstractions that allow for more modular and reusable code. By decoupling function calls from their implementations, function pointers enhance the flexibility and maintainability of your code. The syntax for declaring a function pointer in C requires careful attention to its structure. A function pointer declaration starts with the return type of the function it will point to, followed by an asterisk, and the pointer name enclosed in parentheses. This is crucial because without the parentheses, the compiler might interpret the declaration as a function that returns a pointer rather than a pointer to a function. For example, the declaration int func ptrint. Int defines a pointer named funcptr that can store the address of a function, taking two integer parameters and returning an integer. The parentheses around the pointer name ensure that the asterisk is associated with the pointer rather than the return type. This syntax is essential for matching the function signature, which includes the return type and the types of all parameters. If the function signature does not match, the compiler will generate an error, ensuring type safety when using function pointers. To use a function pointer, you first need to declare a function with a matching signature. For instance, a function like int addend a int b return a plus b can be assigned to a function pointer. Assigning the address of this function to the pointer is straightforward. You can use the address of operator and as in funcptr and add, or simply assign the function name directly, as in funcptr equals add. Both approaches are valid because the function name by itself evaluates to its address. Once assigned, the function pointer can point to any other function that has the same return type and parameter list. This flexibility allows you to create arrays of function pointers or pass functions as arguments to other functions, enabling dynamic behavior in your programs. However, it is critical to ensure that the function signatures match exactly to avoid undefined behavior or runtime errors. Once a function pointer is assigned, you can call the function it points to using the pointer, just like you would call the function directly. For example, if funcptr points to the add function, you can invoke it with int result equals funcptr3 5, which is functionally equivalent to int result equals add3 5. This indirect method of calling functions is particularly useful in scenarios where the exact function to execute is determined at runtime. For instance, in a menu-driven application, different functions can be selected based on user input, and the corresponding function pointer can be used to execute the chosen operation. This approach supports polymorphism-like behavior in C, where the same interface can be used to invoke different implementations. However, it is important to handle function pointers carefully, as mismatched signatures or null pointers can lead to crashes or unpredictable results. Always validate that the pointer is not null before dereferencing it. A practical example of function pointers in action is their use in sorting algorithms. The standard library function qsort demonstrates this by accepting a function pointer to a comparison function. For example, a function like int compare a cint, a int b return a minus b, can be passed to qsort to sort an array in ascending order. By changing the comparison function, you can sort the same array in descending order or based on other criteria, such as the absolute value of elements. This flexibility allows the qsort function to be reused for different sorting needs without modifying its implementation. The function pointer acts as a plugin, enabling the algorithm to adapt to various requirements. This approach not only reduces code duplication, but also makes the code more maintainable and extensible. Function pointers thus play a vital role in creating generic and reusable functions that can handle diverse use cases. The advantages of using function pointers are numerous and significant. They enable dynamic behavior by allowing programs to select and execute functions at runtime, which is essential for applications that need to adapt to changing conditions. This dynamic selection is particularly useful in plugin architectures, where additional functionality can be loaded and integrated at runtime. Function pointers also facilitate modular design by decoupling the code that calls a function from the code that implements it. This separation promotes reusability, as functions can be swapped or extended without altering the calling code. Furthermore, they support event-driven programming, where functions are triggered by specific events, such as user actions or system signals. By abstracting function calls, function pointers reduce code duplication and make the code base easier to manage. They are a cornerstone of advanced C programming, enabling complex behaviors and efficient code organization. In summary, pointers to functions are a fundamental concept in C that unlock a wide range of capabilities for dynamic and flexible programming. They allow functions to be treated as first-class citizens, enabling features like callbacks, polymorphism, and modular design. By mastering the syntax and usage of function pointers, you can write more efficient, reusable, and maintainable code. Their applications extend beyond simple function calls, influencing areas such as sorting algorithms, event handling, and library design. As you practice with examples and explore real-world scenarios, you will gain a deeper understanding of how function pointers can enhance your programming skills. Remember, the key to leveraging function pointers effectively lies in understanding their syntax, ensuring correct function signatures, and using them judiciously to avoid potential pitfalls. With consistent practice, you will become proficient in using this powerful tool to build robust and adaptable C programs. Command line arguments allow users to pass data to a program when it starts. This means that instead of hard-coding values directly into the program, you can provide inputs through the terminal or command prompt. These arguments are accessed through the main function parameters, which are int arg and char star arg square brackets. The arg variable stands for argument count and tells you how many arguments were provided. The arg array holds the actual arguments as strings. This feature is incredibly useful because it allows you to customize how a program behaves without changing the source code itself. For example, a program that processes text files can take the file name as an argument, making it reusable for different files. The main function signature in C is int main int arg char star arg square brackets. This is the standard way to define the entry point of a C program. The arg parameter represents the number of arguments passed to the program, including the program name itself. For instance, if you run a program called /miprogram with 2 arguments, arg would be 3. The arg parameter is an array of character pointers, where each element points to a string representing an argument. The first element, arg0, is always the program name, while the subsequent elements correspond to the user-provided arguments. Understanding this signature is essential for working with command line inputs in C. To access command line arguments, you use the arg array. The first element, arg0, is the name of the program. For example, if you compile and run a program called hello, arg0 would be hello. The next elements, such as arg1, arg2, and so on, contain the arguments provided by the user. These are stored as strings, so you can process them directly or convert them to other data types if needed. It is important to note that arg is a null pointer, which marks the end of the array. This helps in looping through the arguments safely without exceeding the bounds of the array. Here is an example program that demonstrates how to use command line arguments. The code starts by including the standard input-output header file. The main function takes arg and arg as parameters. Inside the main function, a for loop iterates from 0 to arg-1, printing each argument along with its index. For instance, if the program is run with the arguments hello and world, the output would display argument 0, program argument 1, hello, and argument 2, world. This simple loop allows you to access and process all the arguments provided by the user. Handling multiple arguments requires a loop to process each one. For example, if a program is called with the arguments hello and 123, argv1 would be hello and argv2 would be 123. It is crucial to validate the value of arg to ensure that the program does not attempt to access out-of-bounds elements in the argv array. This can be done by checking if arg is greater than or equal to the expected number of arguments. By doing so, you prevent runtime errors and make your program more robust. Additionally, handling edge cases, such as when no arguments are provided, enhances the user experience. Command line arguments are widely used in various scenarios. One common use case is file operations, where a program might take input and output file names as arguments. For example, a copy program could be called with copy file 1, txt file 2, txt, to copy the contents of one file to another. Another use is configuration settings, where flags like verbose or help can be passed to modify the program's behavior. These arguments allow programs to be more flexible and adaptable to different user needs. They also enable automation, as scripts can pass arguments to programs without manual intervention. Error handling is an essential part of working with command line arguments. A common practice is to check if the number of arguments meets the expected minimum. For example, if a program requires a file name, you can check if arg is less than 2 and display a usage message. This helps users understand how to correctly use the program. Additionally, you should handle invalid inputs, such as non-existent files or incorrect data types. By implementing proper error checks, you make your program more user-friendly and reduce the likelihood of crashes or unexpected behavior. When working with command line arguments, there are several practical tips to keep in mind. To convert string arguments to numbers, you can use functions like array or strtal, which are part of the standard library. Avoid hard-coding values into your program, as this limits its flexibility. Instead, rely on arguments to provide necessary inputs, testing edge cases, such as when no arguments are provided or when extra arguments are given, ensures that your program handles all possible scenarios gracefully. These practices lead to more reliable and maintainable code. Command line arguments significantly enhance the flexibility and usability of C programs. By mastering the use of arc and argv, you can create programs that adapt to different inputs without requiring code changes. This capability is invaluable in scenarios where dynamic input is necessary, such as processing files or configuring settings. Applying these concepts allows you to build robust and user-friendly applications that meet a wide range of requirements. As you continue to explore C programming, understanding command line arguments will become a fundamental skill in your toolkit. Errors in C programs can be categorized into three main types: syntax errors, runtime errors, and logical errors. Syntax errors occur when the code violates the rules of the C language and are typically caught by the compiler. Runtime errors happen during program execution, such as division by zero, which causes a crash, or accessing null pointers, which leads to undefined behavior. Logical errors are more subtle and occur when the program runs, but produces incorrect results due to flawed algorithms or incorrect logic. Proper error handling is essential because it enhances the reliability of the program, ensuring it can recover from unexpected situations and provide a better user experience. Common error types include division by zero, which can be avoided with checks, null pointers that may cause crashes if not validated, and memory leaks that occur when allocated memory is not properly freed. Understanding these errors helps developers write more robust and maintainable code. The C programming language provides functions like pairer and strarer to help developers identify and diagnose errors. The pairer function is used to print a descriptive error message to the standard error stream, which is useful for debugging. For example, when a system call fails, pairer can display a message that explains the error in human-readable terms. The strarer function, on the other hand, returns a string that describes the last error encountered based on the value of the global variable errno. This allows programmers to retrieve error messages programmatically. For instance, if a file cannot be opened, calling pairer with a custom message like file open failed will display both the message and the system-specific error description. These functions are invaluable for understanding the root cause of errors during development and troubleshooting. One of the most critical practices in C programming is to always check the return values of functions, especially those that can fail, such as fopen for file operations or malloc for memory allocation. Failing to check these return values can lead to undefined behavior, crashes, or data corruption. For example, if a call to fopen returns null, it indicates that the file could not be opened, and the program must handle this situation gracefully. This can involve logging an error message, terminating the program, or attempting an alternative action. Using conditional checks with if statements allows the program to respond appropriately to errors, ensuring that it does not proceed with invalid data or states. By implementing these checks, developers can create more resilient applications that handle unexpected scenarios without abrupt termination. Debugging is an essential skill for any C programmer, and there are several techniques to identify and fix issues in code. One of the simplest methods is using the print function to trace the execution flow of the program, which helps pinpoint where the code deviates from expected behavior. However, for more complex issues, tools like the GNU debugger or GDB offer advanced capabilities. GDB allows developers to step through code line by line, inspect variable values, and set breakpoints to examine specific sections of the program. Another powerful technique is the use of assertions with the assert function, which checks whether a condition holds true during testing. If the condition fails, the program terminates and displays an error message, helping to quickly identify logical errors. These debugging strategies, when combined, can significantly reduce the time spent identifying and resolving issues. Effective debugging often involves isolating problematic code sections to narrow down the source of an error. This can be done by commenting out parts of the code or using a modular approach to test individual functions. Modern debuggers also provide features like breakpoints, which pause the program at specific lines, and watch variables, which monitor the values of key variables during execution. Reviewing stack traces is another crucial practice, as they show the sequence of function calls leading up to an error. This is particularly useful for runtime errors, as it helps trace the origin of the problem. By systematically analyzing these elements, developers can efficiently diagnose and resolve issues, leading to more stable and reliable software. Handling file I/O errors is a common challenge in C programming, as file operations can fail for various reasons. The first step is to always check the return value of the open function, which returns null if the file cannot be opened. Once a file is opened, it is important to use functions like fief to check for the end of the file, and fairer to detect any errors during reading or writing. For example, if a file read operation fails, fairer will return a non-zero value, indicating the need for error handling. After completing file operations, it is crucial to close the file using fclose to release system resources and prevent file descriptor leaks. Proper handling of file I/O ensures that the program can recover from errors and maintain data integrity. Memory management in C requires careful attention, as improper handling can lead to memory leaks and other critical issues. The malloc and calloc functions allocate memory dynamically, but they may return null if the system cannot fulfill the request. Ignoring this return value can result in dereferencing a null pointer, causing a crash. To prevent memory leaks, developers must ensure that every allocated block of memory is freed using the free function once it is no longer needed. Tools like Valgrind can be used to detect memory leaks by monitoring memory usage during program execution. By adopting disciplined memory management practices, developers can avoid common pitfalls and ensure efficient use of system resources. Signal handling in C allows programs to respond to unexpected events, such as crashes or interruptions, by defining custom handlers. The signal function and its more advanced counterpart, SIGAction, are used to register functions that execute when specific signals are received. For example, the SIGSEGV signal is generated when a program attempts to access invalid memory, leading to a segmentation fault. By setting up a handler for this signal, the program can log an error message or perform cleanup before terminating. This technique can prevent the program from crashing abruptly and provide valuable information for debugging. However, signal handlers should be used cautiously, as they can introduce complexity and may not be suitable for all types of errors. Adopting best practices practices for error handling ensures that code is both robust and maintainable. One key practice is to document error codes and their meanings, making it easier for developers to understand and resolve issues. Using enums or constants to represent error codes improves code readability and reduces the risk of typos. Additionally, providing user-friendly error messages helps end users understand what went wrong without exposing sensitive information. For instance, instead of displaying a cryptic system error, the program can show a message like "failed to save file. Please check the disk space." By following these guidelines, developers can create applications that are not only reliable, but also easier to debug and maintain. In conclusion, effective error handling is a fundamental aspect of writing reliable C programs. It helps prevent failures by anticipating and managing potential issues before they escalate. Debugging is an essential part of the development process, as it allows developers to identify and fix problems systematically. By combining tools like Parer, GDB, and Valgrind with best practices such as checking return values and using assertions, programmers can build robust applications. Continuous learning and attention to detail in error handling and debugging contribute to the creation of high-quality software that performs well under various conditions. Recursion is a programming technique where a function calls itself. This approach allows a function to solve a problem by breaking it down into smaller, similar subproblems. For example, instead of writing a loop to handle repetition, a recursive function can invoke itself with modified parameters until it reaches a base case. This method is particularly useful for problems that have a natural hierarchical or nested structure, such as traversing trees or calculating factorials. However, recursion requires careful design to ensure it terminates properly. Without a well-defined base case, the function could call itself indefinitely, leading to infinite recursion and eventually a stack overflow. Each recursive call creates a new stack frame. When a function calls itself, the computer reserves a new section of memory called a stack frame to store the function's local variables, parameters, and return address. This process continues as the function calls itself with modified parameters, each time adding a new frame to the stack. The base case is crucial because it provides a condition that stops the recursion. allowing the stack frames to unwind and return the results. If the recursion depth becomes too large, the stack can exceed its memory limit, resulting in a stack overflow error. This is why recursion is generally not recommended for very deep or unbounded problems. Here is an example of a recursive function to calculate the factorial of a number. The function starts by checking if the input value is 0, which is the base case. If so, it returns 1, as the factorial of 0 is defined to be 1. Otherwise, the function multiplies the current number by the factorial of the number -1. For instance, when calculating the factorial of 5, the function breaks it down into 5 multiplied by 4, which then becomes 4 multiplied by 3, and so on until it reaches the base case. This step-by-step breakdown illustrates how recursion simplifies complex calculations by reducing them to smaller, manageable steps. Another common example of recursion is the Fibonacci sequence. The function for this sequence checks if the input value is 0 or 1, returning the same value in those cases. For larger values, the function returns the sum of the 2 preceding numbers in the sequence. However, this approach is inefficient because it recalculates the same values multiple times. For example, calculating the Fibonacci of 5 involves repeated calls to the Fibonacci of 3 and 2, leading to exponential time complexity. This inefficiency makes recursion less suitable for large inputs in this case, and alternative methods like dynamic programming or iteration are often preferred. Recursive functions have several key characteristics that distinguish them from iterative solutions. First, they must include a base case to prevent infinite recursion. Without this, the function will keep calling itself indefinitely. Second, the parameters of each recursive call should move the function closer to the base case, ensuring progress toward termination. Third, each call adds a new stack frame, which can lead to increased memory usage. Finally, deep recursion can cause stack overflow errors, making it essential to balance recursion depth with the available memory. These traits highlight the importance of careful design when implementing recursive functions. Recursion offers several advantages that make it a valuable tool in programming. It simplifies complex problems by allowing functions to express solutions in terms of smaller, similar problems. This often results in cleaner and more readable code, especially for tasks like tree traversals or divide and conquer algorithms. Additionally, recursion eliminates the need for explicit stack management, as the call stack automatically handles the state of each function call. This can make the code easier to write and maintain, particularly for problems with inherently recursive structures. However, these benefits come with trade-offs that must be considered. Despite its advantages, recursion has several drawbacks that limit its use in certain scenarios. The primary issue is higher memory consumption due to the stack frames created for each recursive call. This can be a problem for deep recursion, where the stack may exceed its capacity. Additionally, recursive functions often run slower than their iterative counterparts due to the overhead of function calls. The risk of stack overflow is another significant concern, as excessive recursion can crash a program. These limitations mean that recursion is not always the best choice for performance-critical applications, and alternative approaches may be necessary. Recursion is most appropriate for problems that have a natural recursive structure. For example, tasks involving trees, graphs, or nested data structures often benefit from recursive solutions. It is also useful when the problem can be divided into smaller, identical subproblems, such as in sorting algorithms like quicksort or merge-sort. However, recursion is best suited for cases where the depth of recursion is manageable and the base case is well defined. In situations where performance or memory usage is a priority, an iterative approach may be more efficient. Understanding the strengths and limitations of recursion helps determine when it is the optimal solution. In summary, recursion is a powerful technique for solving problems by breaking them into smaller, self-similar parts. It relies on a base case to terminate the process and uses the call stack to manage function calls. While it can lead to elegant and readable code, it also requires careful handling to avoid issues like infinite recursion or stack overflow. By understanding the trade-offs between recursion and iteration, programmers can choose the most appropriate method for their specific needs. Recursion remains a fundamental concept in computer science, offering a unique perspective on problem solving that complements traditional iterative approaches. Bitwise operations allow programmers to manipulate individual bits within binary numbers. Each bit represents a single binary digit either 0 or 1, and these operations work directly on these units. This level of control is essential in scenarios where precision and efficiency are critical. For example, in low-level programming, developers can directly interact with hardware components, such as configuring registers or managing memory at the bit level. Optimization is another key area where bitwise operations shine, as they often execute faster than arithmetic operations. In the context of the C programming language, these operations are foundational for tasks like data compression, where bits are rearranged to reduce storage size, encryption algorithms that transform data at the bit level for security, and device drivers that communicate with hardware devices. Understanding bitwise operations is a crucial skill for any C programmer aiming to work with system-level programming or performance-critical applications. In C, several bitwise operators are available to perform operations on binary data. The AND operator compares corresponding bits of two values and returns a 1 only if both bits are 1. This is useful for masking, where you want to isolate specific bits. The OR operator returns 1 if at least one of the corresponding bits is 1, making it ideal for setting bits. The XOR operator, which stands for exclusive OR, returns 1 when the bits being compared are different. This is often used for toggling bits or performing simple encryption. The NOT operator inverts all the bits of a value, turning 1s into 0s and vice versa. This is commonly used to create masks for bit manipulation. The left shift operator moves the bits of a number to the left, effectively multiplying the value by 2 raised to the power of the number of shifts. Conversely, the right shift operator moves bits to the right, dividing the value by 2 raised to the power of the number of shifts. These operators are fundamental in C because they enable direct manipulation of binary data, which is essential for tasks requiring high performance or low-level hardware interaction. Common bitwise operations include setting, clearing, toggling, and checking bits. Setting a bit involves using the OR operator with a mask that has a 1 in the position of the bit you want to set. For instance, if you have a variable and you want to ensure the first bit is 1, you can apply a mask of 0x01, which is binary 1. Clearing a bit requires using the AND operator with the inverse of the mask. For example, to clear the first bit, you would use the mask 0 XFE binary 11,111,110 and apply it with the AND operator. Toggling a bit, which switches it between 1 and 0, can be achieved using the XOR operator with the same mask. If the bit is 1, it becomes 0, and if it is 0, it becomes 1. Checking a bit involves using the AND operator with a mask to determine if a specific bit is set. If the result is non-zero, the bit is set, otherwise, it is not. These operations are widely used in programming to manage flags, configure hardware settings, and implement efficient data structures. Bitwise operations have numerous practical applications, particularly in scenarios where efficiency and precision are required. One common use is in flags and bit masks, where a single integer can represent multiple Boolean states. For example, a single byte can hold 8 different flags, each indicating a specific condition. This is highly efficient in terms of memory usage and speed. In data compression, bitwise operations are used to encode and decode information by manipulating bits to reduce the overall size of the data. Hardware control is another critical area, as programmers often need to interact directly with hardware registers, which are typically accessed through bitwise operations. For instance, configuring a microcontroller's input-output pins requires setting or clearing specific bits in a register. Encryption algorithms also rely heavily on bitwise operations to perform transformations on data at the bit level, ensuring security. These applications demonstrate the versatility and power of bitwise operations in solving complex programming challenges. Bit manipulation techniques are essential for optimizing code and handling low-level data. Extracting specific bits from a value can be done using the AND operator with a carefully crafted mask. For example, if you need to isolate the third bit of a number, you can use a mask of 0x0 for binary 100 and apply the AND operator. Shifting bits is another technique that improves performance, as shifting left or right is faster than multiplying or dividing by powers of 2. For instance, shifting a number left by 3 positions is equivalent to multiplying it by 8. The XOR operator can also be used to swap the values of 2 variables without a temporary variable, a technique that is both efficient and elegant. However, this method requires that the 2 variables are distinct. Handling endianness, which refers to the order in which bytes are stored in memory, is another important aspect of bit manipulation. Different systems may store data in little endian or big endian formats, and understanding this is crucial for ensuring compatibility when transferring data between systems. These techniques are vital for writing efficient, portable, and robust code in C. While powerful, bitwise operations can lead to several pitfalls if not used carefully. One common issue is the behavior of right shifts on signed integers, which may result in sign extension. This means that the leftmost bits are filled with ones, potentially altering the value in unexpected ways. Overflow is another concern, as shifting a value beyond the number of bits it occupies can lead to undefined behavior, especially in C, where the language does not specify the outcome. Designing masks incorrectly can also cause problems, as an improperly constructed mask may inadvertently alter bits that should remain unchanged. For example, using a mask that is too broad could corrupt other parts of a value. Additionally, portability issues arise because the behavior of bitwise operations can vary across different platforms. Factors such as the size of integers, endianness, and compiler-specific implementations can affect the outcome. Programmers must be aware of these challenges and test their code thoroughly to avoid unexpected results. Bitwise operations are a powerful tool in the C programming language, offering unparalleled control over data at the binary level. Mastering these operations requires a solid understanding of binary representation and the behavior of each operator. While they can significantly enhance performance and enable low-level hardware interaction, they must be applied with care to avoid bugs and ensure portability. Practicing with real-world scenarios, such as implementing bit masks for flags or optimizing arithmetic operations, can reinforce these concepts. By gaining proficiency in bitwise manipulation, programmers can tackle complex problems in areas like embedded systems, data compression, and encryption. As with any advanced technique, consistent practice and attention to detail are essential for leveraging the full potential of bitwise operations in C. The C Standard Library is a collection of pre-written functions designed to handle common programming tasks. These functions are part of the C programming language standard, ensuring they are available across different platforms and compilers. By using these functions, developers can avoid writing code from scratch, which reduces the complexity of their programs and improves overall efficiency. For instance, instead of manually implementing a function to read user input, you can use the built-in print and scan functions from the stdoh header. The library is organized into headers, which group related functions together. Some of the most frequently used headers include stdoh for input-output operations, stdlib-h for memory management and utility functions, string-h for string manipulation, and math-h for mathematical calculations. These headers provide a structured way to access the library's functionalities, making it easier for programmers to manage and maintain their code. Let us explore some of the most commonly used headers in the C standard library. The stdoh header is essential for input and output operations. It contains functions like print, which allows formatted output to the console, and scanf, which reads input from the user. The stdlib-h header provides functions for memory allocation, such as malloc and free, which dynamically manage memory during program execution. It also includes utility functions like rand for generating random numbers and srand for initializing the random number generator. The string-h header is dedicated to string manipulation, offering functions like strcpy to copy strings, strcat to concatenate them, and strlen to determine their length. Finally, the math-h header contains mathematical functions such as sqrt to compute square roots, pow to raise numbers to a power, and trigonometric functions like sin and cos. Each of these headers serves a specific purpose, enabling programmers to perform a wide range of tasks efficiently. Now, let us focus on some key functions from the stdoh header. The print function is one of the most widely used functions in C. It allows you to output data in a formatted manner, such as printing numbers, strings, or variables. For example, you can use format specifiers like %d for integers or %s for strings to control how the output is displayed. The scant function, on the other hand, reads input from the user, enabling interactive programs. It can parse input based on specified data types, making it useful for collecting user data. In addition to these, the fopen function is used to open files for reading or writing, which is crucial for handling file I/O operations. Once a file is no longer needed, the fclose function should be called to close it, ensuring that all data is properly saved and system resources are released. These functions form the foundation of input and output operations in C, making them indispensable for many applications. The STD-lib H header contains functions for memory management and general utility tasks. One of the most important functions is malloc, which dynamically allocates memory during program execution. This is particularly useful when the required memory size is not known at compile time. However, it is crucial to remember to free the allocated memory using the free function to prevent memory leaks, which can lead to program instability or crashes. The rand function generates pseudo-random numbers, which can be used for simulations or games. However, the sequence of numbers produced by rand is deterministic, so it is common to seed the generator using srand with a value like the current time to achieve different results each run. These functions provide the flexibility to manage memory and generate random values, making them essential tools in many C programs. The string H header offers a set of functions for manipulating strings. The strcpy function copies the contents of one string to another, but it is important to ensure the destination buffer is large enough to avoid overflow. The strcat function appends one string to the end of another, which is useful for combining strings. The strlen function returns the length of a string, which is helpful for tasks like checking input validity or determining loop boundaries. Finally, the strcmp function compares two strings lexicographically, returning a value that indicates whether they are equal or which one comes first in alphabetical order. These functions are fundamental for string handling, but they require careful use to prevent issues like buffer overflows or undefined behavior, which can lead to security vulnerabilities or program crashes. The math-h header contains a variety of mathematical functions that are essential for scientific and engineering applications. The sqrt function computes the square root of a number, which is useful in calculations involving geometry or physics. The pow function raises a number to a specified power, allowing for exponentiation operations. Trigonometric functions like sin and cos are used in calculations involving angles and waves, such as in signal processing or game development. It is important to note that when using these functions, the program must be linked with the math library using the LM flag during compilation. This is because the math functions are not included by default and the linker needs to know where to find them. These functions expand the capabilities of C, enabling complex mathematical computations that would otherwise require custom implementations. To use the C standard library effectively, there are several best practices to follow. First, always include the appropriate header files for the functions you need. For example, if you are using malloc, you must include stdlib.h. Second, check the return values of functions, especially those that can fail, such as malloc. If malloc returns a null pointer, it indicates that memory allocation failed, and the program should handle this gracefully. Third, refer to man pages for detailed documentation on each function. Man pages provide comprehensive information about function parameters, return values, and usage examples. Finally, avoid undefined behavior by adhering to the rules of the language. For instance, never access array elements out of bounds, as this can lead to unpredictable results. By following these practices, programmers can write more reliable and maintainable code, leveraging the power of the standard library without introducing errors. In conclusion, the C standard library is a powerful tool that enhances productivity and code reliability. By providing pre-written functions for common tasks, it allows developers to focus on solving problems rather than implementing basic operations. Mastering these functions is essential for efficient C programming, as they form the foundation of many applications. Practicing with functions from different headers will help build proficiency and deepen your understanding of the language. Whether you are working on simple console applications or complex systems, the standard library offers the tools needed to write robust and efficient code. Continual practice and exploration of these functions will enable you to become a more skilled and confident C programmer. Linked lists are a type of dynamic data structure that allows for the storage of collections of elements in a flexible manner. Unlike static data structures such as arrays, linked lists do not require a predefined size, making them highly adaptable to changing data needs. Each element in a linked list, known as a node, contains two main components: the data itself and a pointer that references the next node in the sequence. This structure enables efficient manipulation of data by allowing insertions and deletions without the need to shift elements, which is a common requirement in arrays. These characteristics make linked lists particularly useful in scenarios where data is frequently added or removed, such as in the implementation of stacks, queues, and dynamic memory allocation. Their flexibility and efficiency in handling dynamic data make them a fundamental concept in computer science and programming. In the C programming language, linked lists are implemented using a structure definition. The basic building block is a struct that contains a data field and a pointer to the next node in the list. For example, a struct node might have an integer data field and a pointer to another struct node, creating a chain of nodes. This structure allows for the creation of nodes that can be dynamically allocated in memory using functions like malloc. The head pointer, which is typically the starting point of the list, points to the first node and serves as the entryway to traverse the entire linked list. By dynamically allocating memory, programmers can manage the list's size and structure as needed, which is especially useful in applications where the amount of data is unknown or variable. This approach also ensures that memory is used efficiently, as nodes are created only when necessary. The fundamental operations of linked lists include insertion, deletion, traversal, and search. Insertion involves adding a new node to the list, which can be done at the beginning, the end, or at a specific position. For instance, inserting a node at the beginning requires updating the head pointer to point to the new node, while inserting at the end involves traversing the list to find the last node and adjusting its pointer. Deletion, on the other hand, requires modifying the pointers of the surrounding nodes to bypass the node being removed, ensuring the list remains intact. Traversal is the process of accessing each node in sequence, starting from the head and following the next pointers until the end of the list is reached. Search operations involve comparing the data of each node to a target value, allowing for the retrieval of specific elements. These operations form the core of linked list manipulation and are essential for building and maintaining dynamic data structures. Linked lists come in several types, each with distinct characteristics. The most basic is the singly linked list, where each node contains a pointer to the next node in the sequence. This structure allows for unidirectional traversal, making it suitable for applications that require simple data access. A doubly linked list extends this concept by adding a pointer to the previous node, enabling bidirectional traversal. This feature is particularly useful in scenarios where nodes need to be accessed in both forward and backward directions, such as in certain types of data storage systems. The circular linked list is another variation, where the last node points back to the first node, creating a loop. This structure is often used in applications requiring continuous data access, such as round-robin scheduling algorithms. Each type of linked list offers unique advantages, and the choice of structure depends on the specific requirements of the application. Compared to arrays, linked lists offer several advantages, particularly in scenarios where dynamic data handling is required. One of the key benefits is their ability to grow or shrink in size as needed, eliminating the need to predefine a fixed size. This flexibility is especially valuable in environments where the amount of data is unpredictable or subject to change. Additionally, linked lists allow for efficient insertions and deletions, as these operations do not require shifting elements, unlike arrays where such operations can be time-consuming. Memory efficiency is another advantage, as linked lists allocate memory only when new nodes are added, reducing waste. However, it is important to note that linked lists have some drawbacks, such as the additional memory required for storing pointers and the lack of direct access to elements, which can make certain operations slower compared to arrays. Understanding these trade-offs is crucial for selecting the appropriate data structure for a given task. Linked lists are widely used in the implementation of various data structures and real-world applications. For example, they form the basis of stacks and queues, where elements are added and removed in a specific order. In real-time systems, linked lists provide the flexibility needed to manage dynamic data, such as in event-driven programming or resource allocation. Operating systems often use linked lists for memory management, allowing for efficient allocation and deallocation of memory blocks. Additionally, linked lists are employed in hash tables to handle collisions and in graphs to represent adjacency lists, which describe the connections between nodes. These applications highlight the versatility of linked lists in solving complex problems and their importance in modern software development. By leveraging the strengths of linked lists, programmers can create more efficient and scalable solutions. In conclusion, linked lists are a foundational concept in computer science and programming, offering a powerful way to handle dynamic data. Mastering the operations of inserting, deleting, traversing, and searching nodes is essential for building advanced data structures and algorithms. While linked lists have advantages over arrays, such as dynamic size and efficient insertions, they also come with trade-offs, including increased memory usage and slower access times. Understanding these trade-offs enables programmers to make informed decisions when choosing between linked lists and other data structures. Practicing the implementation of linked lists in C is crucial for developing a deep understanding of their functionality and applications. By repeatedly working with linked lists, students can enhance their problem-solving skills and become more proficient in handling complex data scenarios. Stacks and queues are fundamental linear data structures that help organize and manage collections of elements in a specific order. These structures are essential for handling data in a way that ensures predictable and efficient access. A stack operates on the LIFO principle, which stands for last in, first out. This means the last element added to the stack is the first one to be removed, much like a stack of plates where you take the top plate first. In contrast, a queue follows the FIFO principle, or first in, first out, where the first element added is the first to be removed, similar to a line of people waiting for a service. These principles make stacks and queues invaluable in solving real-world problems such as task scheduling, where queues manage processes in the order they arrive, and memory management, where stacks handle function calls and local variables in programs. Understanding these structures is a cornerstone of efficient algorithm design and system programming. A stack is a collection of elements that supports several key operations. The push operation adds an element to the top of the stack, while the pop operation removes the top element. The peek or top operation allows you to view the element at the top without removing it. Additionally, the isEmpty or isFull operations check whether the stack is empty or has reached its maximum capacity. These operations make stacks ideal for scenarios where you need to track the most recent data, such as in recursion, where each function call is pushed onto the stack and popped off when the function completes. Stacks are also used in expression evaluation, such as converting infix notation to postfix notation, and in backtracking algorithms, where you need to revisit previous states. Their simplicity and efficiency make them a powerful tool in both theoretical and practical programming contexts. A cue, on the other hand, is a collection of elements that supports operations such as in-cue, DQ, front, and is empty or is full. The in-cue operation adds an element to the rear of the cue, while the DQ operation removes the element from the front. The front operation lets you view the element at the front without removing it. These operations ensure that elements are processed in the order they were added, which is crucial for applications like task scheduling in operating systems, where processes are handled in the sequence they arrive. Cues are also used in print queues, where documents are printed in the order they are submitted, and in breadth-first search algorithms, where nodes are explored level by level. The FIFO principle of queues ensures fairness and order, making them indispensable in scenarios where the sequence of processing is critical. Implementing stacks in C can be done using either arrays or linked lists, each with its own advantages and limitations. Array-based stacks are straightforward to implement because they use a fixed-size array, making it easy to manage the stack's top index. However, this approach has a drawback. The maximum size of the stack is predetermined, leading to potential overflow if the stack exceeds its capacity. Overflow occurs when a push operation is attempted on a full stack, which can cause program crashes or data loss. In contrast, linked list-based stacks offer dynamic memory allocation, allowing the stack to grow or shrink as needed. This flexibility is achieved using functions like malloc to allocate memory for new nodes and free to release memory when elements are popped, while linked lists provide more scalability. They require additional overhead for memory management, making them slightly more complex to implement than array-based stacks. Queues in C can also be implemented using arrays or linked lists, each approach having distinct trade-offs. Array-based queues are efficient for fixed-size scenarios, but can suffer from wasted space if the queue is not fully utilized. To optimize space, circular arrays are often used, where the rear pointer wraps around to the beginning of the array once it reaches the end. This prevents the queue from appearing full when there is still available space. However, array-based queues are still susceptible to overflow if the maximum size is exceeded. Linked list-based queues, on the other hand, dynamically allocate memory for each element, eliminating at the risk of overflow. This approach allows the cue to handle an arbitrary number of elements, but it requires careful management of pointers and memory to avoid leaks. Both implementations have their place, and the choice depends on the specific requirements of the application, such as memory constraints or the need for dynamic resizing. Stacks have a wide range of applications that highlight their usefulness in programming. One common use is in implementing undo and redo functionality in text editors, where each action is pushed onto the stack, and undo operations pop the most recent action. Stacks are also essential in parsing expressions, such as converting infix notation to postfix notation, where operators and operands are managed using stack operations. In recursion, the call stack keeps track of function calls, ensuring that each function returns to the correct point in the program. Additionally, stacks play a critical role in memory management, as the call stack in programs stores local variables and return addresses. These applications demonstrate how stacks enable efficient and organized data handling, making them a vital component of modern software development. Queues are equally vital in various applications that require ordered processing. In operating systems, job scheduling algorithms use queues to manage processes, ensuring that each task is executed in the order it was received. Networking systems rely on queues to buffer data packets, allowing for smooth transmission even when there are fluctuations in data flow. Breadth-first search algorithms in graph theory use queues to explore nodes level by level, ensuring that all nodes at a given depth are processed before moving to the next level. Print queues in multi-user systems manage document submissions, printing them in the order they are received. These examples illustrate how queues provide a reliable and systematic way to handle tasks, making them a cornerstone of both software and hardware systems. When comparing stacks and queues, the key difference lies in their access principles. Stacks follow the LIFO principle, meaning operations are performed on a single end, known as the top. This makes stacks ideal for scenarios where the most recent data needs to be accessed first, such as in recursion or expression evaluation. Queues, on the other hand, follow the FIFO principle, with operations performed on both ends, adding elements to the rear and removing them from the front. This makes queues suitable for situations requiring sequential processing, such as task scheduling or buffering. The choice between a stack and a queue depends on the specific needs of the application. Stacks are preferred for nested or hierarchical operations, while queues are better suited for managing tasks in a linear, ordered manner. Understanding these distinctions allows programmers to select the most appropriate data structure for their problem. Common errors when working with stacks and queues include overflow and underflow, which can lead to program instability if not handled properly. Stack overflow occurs when a push operation is attempted on a full stack, often due to a fixed size array implementation. To mitigate this, using a linked list-based stack allows dynamic memory allocation, preventing overflow by expanding the stack as needed. Stack underflow, on the other hand, happens when a pop operation is performed on an empty stack, leading to undefined behavior. To prevent underflow, it is essential to check the stack's status using isempty before performing any operation. Similarly, queues can experience overflow when the rear pointer reaches the end of the array, and underflow when the front pointer moves past the last element. Implementing proper checks and using circular arrays or linked lists can help avoid these issues, ensuring the reliability and robustness of the data structures. In conclusion, stacks and queues are foundational data structures that play a critical role in managing data flow in programming. Their ability to organize elements in a specific order makes them indispensable for solving a wide range of problems, from task scheduling to expression evaluation. Understanding their operations, implementations, and applications is essential for developing efficient and scalable solutions. Choosing between stacks and queues depends on the requirements of the problem at hand, with stacks excelling in nested or hierarchical scenarios, and queues in sequential processing. Practicing the implementation of these structures in C reinforces theoretical knowledge and builds practical skills. By mastering stacks and queues, programmers can enhance their ability to design and optimize algorithms, making them more effective in both academic and professional settings. Sorting algorithms are essential tools for arranging data in a specific order, either ascending or descending. This process is fundamental in computer science because it allows us to organize information systematically. When data is sorted, it becomes much easier to retrieve, analyze, and process. For example, imagine Imagine searching for a name in a phone directory that is not sorted versus one that is. The latter would be significantly faster. Common sorting algorithms include bubble sort, selection sort, insertion sort, merge sort, and quick sort. Each of these algorithms has its own approach to ordering data, and they vary in efficiency depending on the size and nature of the dataset. Understanding these algorithms helps us make informed decisions about which one to use in different scenarios. Bubble sort is one of the simplest sorting algorithms to understand and implement. It works by repeatedly comparing adjacent elements in the array and swapping them if they are in the wrong order. This process continues until the entire list is sorted, with each pass pushing the largest unsorted element to its correct position. For instance, if we have an array like 5, 3, 8, 4, the first pass would compare 5 and 3, swap them, then 5 and 8 no swap, then 8 and 4, swapping them. After multiple passes, the array becomes 3, 4, 5, 8. However, bubble sort has a time complexity of O of n squared in average and worst cases, making it inefficient for large datasets. Despite this, it is often used in educational settings to teach the basics of sorting due to its simplicity. Selection sort is another straightforward algorithm that works by finding the smallest element in the unsorted portion of the array and swapping it with the first unsorted element. This process is repeated for each position in the array, gradually building up the sorted section. For example, in the array 6, 2, 9, 1, the first iteration would find 1 as the smallest and swap it with 6, resulting in 1, 2, 9, 6. The next iteration would find 2 as the smallest in the remaining unsorted part and leave it in place. Selection sort also has a time complexity of O of n squared in all cases, which means it performs the same regardless of the initial order of the data. While it is slightly more efficient than bubble sort in terms of the number of swaps, it is still not suitable for large datasets. Insertion sort is a practical algorithm for small or nearly sorted datasets. It works by building the sorted array one element at a time, inserting each new element into its correct position. This is similar to how a person might sort a hand of cards by picking up each card and placing it in the right spot. For instance, in the array 4, 2, 6, 1, the algorithm would start with 4 as the sorted part, then insert 2 before 4, then then 6 after 4, and finally 1 at the beginning. Insertion sort has a time complexity of O of n squared in average and worst cases, but can perform in O of n time if the data is already nearly sorted. This makes it a good choice for small data sets, or when the data is mostly sorted, as it can be faster than other algorithms in such scenarios. Merge sort is a divide and conquer algorithm that efficiently sorts large data sets. It works by recursively splitting the array into smaller halves, sorting each half, and then merging the sorted halves back together. For example, an array like 3, 1, 4, 2 would be split into 3, 1, and 4, 2, each of which is further split until individual elements are reached. The merging process then combines the sorted subarrays into a single sorted array. Merge sort has a consistent time complexity of O of n log n in all cases, making it reliable for large data sets. However, it requires additional memory for the merging step, which can be a drawback in memory-constrained environments. Its stability, meaning it preserves the relative order of equal elements, also makes it a preferred choice in certain applications. Quicksort is another divide and conquer algorithm that is widely used for its efficiency in practice. It works by selecting a pivot element and partitioning the array into 2 subarrays, one containing elements less than the pivot and the other containing elements greater than the pivot. The algorithm then recursively sorts the subarrays. For example, in the array 5, 3, 8, 4, if we choose 5 as the pivot, the left subarray would be 3, 4, and the right would be 8. The process continues until the entire array is sorted. Quicksort has an average time complexity of O of n log n, making it one of the fastest sorting algorithms for large data sets. However, its worst case time complexity is O of n squared, which occurs when the pivot is poorly chosen, such as when the array is already sorted. To mitigate this, strategies like choosing a random pivot or using the median of 3 method are often employed. When comparing the time complexities of sorting algorithms, it is important to consider their performance characteristics. Algorithms like bubble sort, selection sort, and insertion sort have O of n squared time complexity, which makes them suitable for small data sets where the overhead of more complex algorithms is not justified. On the other hand, merge sort and quicksort have O of n log n time complexity, which is significantly faster for large data sets. However, the choice of algorithm also depends on factors like memory constraints, stability requirements, and the nature of the data. For example, merge sort is stable and consistent, but uses more memory, while quick sort is efficient but not stable. Understanding these trade-offs helps in selecting the most appropriate algorithm for a given problem. Choosing the right sorting algorithm involves analyzing the specific requirements of the task at hand. For small data sets, bubble sort or insertion sort may be sufficient due to their simplicity and low overhead. Merge sort is ideal when stability and consistent performance are critical, such as in applications where the relative order of equal elements must be preserved. Quick sort is often preferred for its average case efficiency, making it a go-to choice for many real-world applications. Additionally, factors like the initial state of the data, whether it is nearly sorted or completely random, can influence the decision. For instance, insertion sort excels with nearly sorted data, while quick sort benefits from a well-chosen pivot. By considering these factors, we can optimize both the time and space efficiency of our sorting solutions. In conclusion, sorting algorithms are foundational to data organization and efficient computation. They enable us to manage and process data effectively, from small-scale problems to large, complex data sets. Understanding the trade-offs between time complexity, space requirements, and stability is crucial for selecting the right algorithm. By practicing the implementation and analysis of these algorithms, we enhance our problem-solving skills and deepen our understanding of computational efficiency. Whether you are working on a simple project or a large-scale application, mastering sorting algorithms is an essential step in becoming a proficient programmer. Searching algorithms are methods used to locate specific elements within data structures, such as arrays, lists, or trees. These techniques are essential in programming because they enable efficient data retrieval, which is critical for optimizing performance in applications ranging from database queries to real-time systems. The importance of searching algorithms lies in their ability to reduce the time required to find information, especially in large data sets. Common types of searching algorithms include linear search, binary search, and hashing. Each of these approaches has unique characteristics that make them suitable for different scenarios. And understanding their strengths and weaknesses is key to effective problem solving in software development. Linear search is the most straightforward searching algorithm, where each element in a data structure is checked one by one in sequence until the target value is found. The process begins at the first element and continues until a match is identified or the end of the structure is reached. This method is particularly useful for small data sets or when the data is unsorted, as it does not require any prior organization of the elements. However, its simplicity comes at a cost. Linear search has a time complexity of O of n, meaning the worst-case scenario involves checking every element in the dataset. Despite its inefficiency for large data, it remains a reliable choice for scenarios where the dataset size is limited, or when the overhead of sorting is not justified. Binary search is a highly efficient algorithm designed for use with sorted arrays. Instead of checking each element sequentially, binary search divides the array into halves and compares the middle element to the target value. If the target is smaller, the search continues in the left half. If it is larger, the search continues in the right half. This process repeats until the target is found or the search space is exhausted. The key advantage of binary search is its logarithmic time complexity, O of log n, which makes it significantly faster than linear search for large datasets. However, this efficiency is contingent on the array being sorted beforehand. Sorting the data may add overhead, but for frequently searched datasets, the initial cost is often justified by the improved search performance. When analyzing the time complexity of searching algorithms, linear search consistently exhibits O of n for both average and worst-case scenarios, as it may need to examine every element. Binary search, on the other hand, operates in O of log n time, which grows much more slowly as the dataset size increases. Hashing, another approach, can achieve O of one time complexity in ideal situations, where data is stored in a hash table and accessed directly via a key. This constant time performance makes hashing highly efficient for certain applications. However, these trade-offs come with their own challenges. Hashing requires additional memory for the hash table, while binary search demands the data be sorted. Choosing the right algorithm depends on factors such as dataset size, frequency of searches, and available resources. Implementing searching algorithms in the C programming language involves writing functions that manipulate arrays and utilize control structures like loops and recursion. For linear search, a function might take an array, its size, and a target value as parameters, then iterate through the elements to find a match. Binary search, by contrast, requires a recursive or iterative approach to divide the array into halves and compare the middle element. Key C concepts such as arrays, loops, and recursion are essential for these implementations. Developers must also consider edge cases, such as empty arrays, where the function should return an appropriate value, or duplicate elements, which may require additional logic to handle multiple matches. Proper testing of these scenarios ensures robust and reliable code. Each searching algorithm has specific use cases and limitations that influence their suitability for different tasks. Linear search is practical for small data sets or when the data is unsorted, as it does not require preprocessing. It is also easier to implement and understand, making it a good choice for beginners. Binary search, however, excels in large, sorted datasets, offering much faster search times. Its primary limitation is the requirement for sorted data, which may necessitate additional sorting steps. Hashing provides the fastest access times, but relies on a well-designed hash function to avoid collisions. Understanding these trade-offs allows programmers to select the most appropriate algorithm for their specific needs, balancing factors such as time, space, and data structure constraints. Searching algorithms are fundamental to data manipulation and are widely used in software development to retrieve information efficiently. The choice of algorithm depends on the characteristics of the dataset, such as size, structure, and whether it is sorted. Practicing the implementation of linear and binary search in C helps reinforce these concepts and develops problem-solving skills. By understanding the strengths and limitations of each approach, programmers can optimize their code for performance and adaptability. As data continues to grow in complexity, mastering these foundational techniques becomes increasingly important for building efficient and scalable applications. A function pointer is a variable that stores the address of a function. This allows you to call functions indirectly, which is particularly useful when you need to pass functions as arguments to other functions, or when implementing callback mechanisms. The syntax for declaring a function pointer is return type followed by an asterisk, then the pointer name in parentheses, and finally the parameter types. For example, int func ptrint, int, and add. This line declares a function pointer called funcptr that points to a function which takes two integers as parameters and returns an integer. By using function pointers, you can dynamically decide which function to execute at runtime, enabling powerful techniques like polymorphism and event-driven programming. Pointer arithmetic allows you to manipulate memory addresses by adding or subtracting values to a pointer. When you increment a pointer, it moves by the size of the data type it points to. For instance, if you have an integer pointer, adding 1 to it moves the address by the size of an integer, which is typically 4 bytes. This is why the expression ptr plus equals 2 in an array of integers points to the third element, not the second. Pointer arithmetic is particularly useful for traversing arrays and dynamically allocated memory. However, it is important to ensure that the pointer remains within the bounds of the allocated memory block to avoid undefined behavior. This technique is fundamental for efficient memory management and low-level programming tasks. Pointers and arrays are closely related in C when you use an array name in an expression. It decays into a pointer to its first element. This means that array indexing can be implemented using pointer arithmetic. For example, the expression array is equivalent to r plus. This relationship allows you to access array elements using either notation. For multi-dimensional arrays, pointers to pointers are often used to represent dynamic two-dimensional structures. For instance, a pointer to a pointer can be used to create a matrix where each row is dynamically allocated. Understanding this connection between pointers and arrays is essential for working with complex data structures and optimizing memory usage. A void pointer or void is a special type of pointer that can point to data of any type. However, because it does not have a specific data type, you cannot dereference it directly. Instead, you must cast it to a specific type before accessing the data it points to. For example, if you have a void pointer pointing to an integer, you must cast it to an int before retrieving the value. This flexibility makes void pointers useful in functions that need to handle multiple data types, such as memory copy functions or sorting routines. However, this power comes with responsibility, as improper casting can lead to data corruption or runtime errors. Always ensure that the cast matches the actual data type stored at the memory address. Advanced pointer concepts include function pointers for callbacks and polymorphism, pointer to pointer for dynamic two-dimensional arrays, and the use of const with pointers to enforce immutability. Function pointers allow you to pass functions as arguments, enabling dynamic behavior in programs. A pointer to a pointer is often used to manage complex data structures, such as dynamically allocated matrices. When using const with pointers, you can specify whether the pointer itself is constant, the data it points to is constant, or both. This helps prevent unintended modifications and improves code safety. Additionally, it is crucial to manage memory carefully to avoid issues like memory leaks, where allocated memory is not freed, or dangling pointers, which point to memory that has already been deallocated. Proper pointer management is key to writing reliable and efficient C programs. Mastering pointers is essential for efficient memory management. In C, they provide direct access to memory, allowing you to optimize performance and handle complex data structures. Advanced concepts like function pointers and void pointers expand the flexibility of your programs, enabling features such as generic functions and dynamic behavior. Practicing pointer arithmetic and array manipulation will help you build more sophisticated data structures and algorithms. Always validate pointers before dereferencing them to prevent runtime errors, such as accessing invalid memory locations. By understanding and applying these concepts, you can write more powerful and efficient C programs. Macros are preprocessor directives that allow code substitution before compilation. These directives are processed by the compiler before the actual code is compiled, enabling the replacement of identifiers with values or code snippets. Macros are defined using the hash define directive, which is followed by the macro name and its replacement. For example, hash define pi 3.14159 replaces every occurrence of pi in the code with the value 3.14159 during preprocessing. This technique is commonly used for defining constants, which makes the code more readable and easier to maintain. Additionally, macros can act as inline functions, allowing code to be expanded directly at the point of use, which can improve performance by avoiding function call overhead. However, it is important to use macros judiciously, as they can introduce subtle bugs due to text substitution. There are two main types of macros: object-like and function-like. Object-like macros replace identifiers with values, much like constants. For example, #define max 100 defines max as a constant with the value 100. These macros are straightforward and useful for defining fixed values. Function-like macros, on the other hand, resemble functions and can take arguments. An example is #define square x left parenthesis, x right parenthesis multiply x right parenthesis, which expands to x multiplied by x. It is crucial to enclose the arguments and the entire macro body in parentheses to avoid unexpected behavior, especially when dealing with expressions that involve operators. For instance, without parentheses, a macro like square x plus 1 would expand to x plus 1 multiplied by x plus 1, which is not the intended result. Proper use of parentheses ensures that the macro behaves as expected. Conditional compilation is a powerful feature that allows developers to control which parts of the code are compiled based on specific conditions. Directives such as #ifdef, #ifndef, #if, #else, and #indiff are used to include or exclude code segments dynamically. For example, #ifdef debug includes debug-specific code only if the macro debug is defined. This capability is particularly useful for managing platform-specific code, enabling or disabling debugging features, and toggling between different configurations. By leveraging conditional compilation, developers can write more flexible and maintainable code that adapts to different environments or requirements. The key conditional compilation directives include #ifdef, which checks if a macro is defined and includes the subsequent code if true. #ifndef checks if a macro is not defined, allowing the inclusion of code in its absence. The #if directive evaluates a constant expression, such as #if version greater than 1, to determine whether to include the following code block. The #else directive provides an alternative code block when the initial condition fails, and #indiff marks the end of a conditional compilation block. These directives work together to create complex conditional logic, enabling precise control over code inclusion and exclusion. Conditional compilation has several practical use cases. One common application is handling platform-specific code, where different implementations are required for various operating systems or hardware architectures. For instance, code for Windows and Linux can be separated using conditional directives. Another use is debugging, where debug logs or assertions are included only when a specific macro is defined. Feature toggles allow developers to enable or disable certain features based on configuration settings, making it easier to manage product variations. Additionally, conditional compilation is used to prevent duplicate includes through include guards. By using hash ifndef, developers ensure that a header file is included only once, avoiding potential redefinition errors. While macros and conditional compilation are powerful tools, they require careful handling to avoid pitfalls. Overuse of macros can lead to reduced code readability and make debugging more challenging, as the preprocessor replaces macros before compilation. It is advisable to use hash undef to remove macros when they are no longer needed, preventing unintended side effects. Documenting the purpose of each macro or condition is essential for maintaining clarity, especially for other developers who may work on the code later. Thorough testing is also critical, as macros can introduce subtle bugs due to their text-based expansion. By following best practices, developers can harness the benefits of macros and conditional compilation without compromising code quality. In summary, macros and conditional compilation are indispensable tools for writing flexible and efficient code. Macros allow for code substitution, making it easier to manage constants and inline functions, while conditional compilation enables dynamic code inclusion based on specific conditions. These features are particularly valuable for adapting code to different environments, managing debugging, and optimizing performance. However, their use requires careful consideration to avoid common pitfalls. By adhering to best practices such as proper documentation, judicious use, and rigorous testing, developers can leverage these tools effectively. Ultimately, mastering macros and conditional compilation enhances the ability to create robust, maintainable, and adaptable software solutions. Memory management in C involves allocating and deallocating memory dynamically. This means that instead of relying solely on static memory allocation, programmers must manually control memory usage during runtime. The key functions used for this process are malloc, calloc, realloc, and free. These functions allow developers to request memory from the system and release it when it is no longer needed. Efficient memory usage is critical for performance and stability because improper handling can lead to resource exhaustion, crashes, or unpredictable behavior. By mastering these techniques, programmers can ensure their applications run smoothly even under heavy workloads. The function malloc takes a size in bytes and returns a pointer to a block of memory of that size. It is the most basic tool for dynamic allocation. The calloc function is similar, but also initializes the allocated memory to 0, making it ideal for arrays or structures where zeroed values are required. Realloc allows resizing an existing memory block, which can be useful when the initial allocation is too small. However, this operation may move the memory block to a new location, so care must be taken to update pointers. Finally, the free function releases the memory back to the system, ensuring it can be reused. These functions form the foundation of dynamic memory management in C. One of the most common pitfalls in memory management is memory leaks, which occur when allocated memory is not properly freed. Over time, these leaks can consume all available memory, causing the program or system to slow down or crash. Dangling pointers are another issue, where a pointer references memory that has already been freed. Accessing such memory can lead to undefined behavior, including crashes or data corruption. Double free errors happen when the same memory block is freed more than once, which can corrupt the heap and cause unpredictable results. Buffer overflows occur when data is written beyond the allocated memory boundaries, potentially overwriting other critical data or executing malicious code. These issues highlight the need for careful programming practices. To avoid these problems, always check the return value of malloc and calloc for null. If the system cannot allocate the requested memory, these functions return a null pointer, and failing to check can lead to crashes. Freeing memory when it is no longer needed is essential to prevent leaks. Use realloc with caution, as it may require copying data to a new location, and ensure that any existing data is preserved. Initializing memory with calloc is particularly important because it sets all bits to 0, reducing the risk of undefined behavior from uninitialized data. These practices form the backbone of safe and efficient memory management. Advanced techniques can further optimize memory usage. Memory pools involve pre-allocating large blocks of memory for frequent small allocations, reducing fragmentation and improving performance. Custom allocators allow developers to tailor memory management to specific application needs, such as real-time systems or games. Tools like Valgrind are invaluable for detecting memory leaks and errors during testing. While C does not have built-in smart pointers, some libraries provide similar functionality to automate memory handling. These techniques, when applied correctly, can significantly enhance the efficiency and reliability of C programs. Effective memory management is critical for C programs, as it directly impacts performance, stability, and security. Avoiding common errors requires discipline, such as always freeing allocated memory and checking for null pointers. Advanced techniques like memory pools and custom allocators can further improve efficiency, but demand a deeper understanding of the underlying system. Practice and thorough testing are essential to ensure robust memory handling. By combining careful coding with the right tools, developers can create reliable and high-performance C applications. File I/O in C allows programmers to interact with external files stored on a computer storage system. This capability is essential for tasks like saving user data, loading configurations, or processing large datasets. The standard library provides functions such as fopen to open files, fclose to close them, fscanf, and fprint for formatted input and output, and freed and fwrite for binary data. Files can be either text-based, which is human-readable and uses characters like letters and numbers, or binary, which stores data in a raw format that machines can process efficiently. Proper error handling is crucial because file operations can fail due to missing files, permission issues, or disk errors. By anticipating these failures, developers can create more reliable programs that handle unexpected situations gracefully. To work with files in C, you must first open them using the fopen function. This function takes two arguments, the file name and the mode. The mode determines how the file will be used. For example, the mode R opens a file for reading, W creates a new file or overwrites an existing one for writing, and appends data to the end of a file without erasing its contents. It is important to note that if the file does not exist and you use R, the operation will fail. Conversely, W and A will create the file if it does not exist. Once you finish working with a file, always close it using F-close. This step ensures that any buffered data is written to the file and that system resources are freed, preventing memory leaks or file corruption. Reading from text files in C can be done using fscanf, which works similarly to the scanf function, but reads from a file instead of the keyboard. For instance, fscanf %d and num reads an integer from the file and stores it in the variable num. This function is useful for parsing structured data like numbers or formatted strings. However, for reading lines of text, the fgets function is more appropriate. It reads a specified number of characters from the file, making it ideal for processing line-by-line data, such as logs or configuration files. To determine when you have reached the end of the file, you can check for the end of file indicator using FIF. This helps prevent infinite loops or incorrect processing of data beyond the file's actual content. Writing to text files in C is achieved through functions like fprint, which functions like the print statement, but outputs to a file instead of the screen. For example, fprint value %d\n. Num writes the value of num to the file in a human-readable format. This is useful for generating reports, saving user input, or logging program activity. Another function, fputs, allows you to write strings directly to a file without formatting. While these functions are convenient, it is important to remember that data written to a file may be stored in a buffer and not immediately written to disk. To ensure that all data is saved, especially in critical applications, you can use flush to force the buffer to be written. This is particularly important in scenarios where the program might terminate abruptly, or when real-time data recording is required. Binary file operations in C involve reading and writing data in its raw form, which is not human-readable, but is highly efficient for machines. This approach is ideal for storing complex data types like structures, images, or audio files. The freed function reads a specified number of elements from a file, each of a given size, into a memory buffer. Similarly, fwrite writes data from a buffer to a file. For example, you can use these functions to save the contents of a structure directly to a file, preserving its exact memory layout. This method is faster and more space efficient than text-based storage, but it requires careful handling to ensure compatibility between the writing and reading programs. Binary files are commonly used in applications where performance and data integrity are critical. File positioning functions allow you to control where in a file the next read or write operation will occur. The fseek function moves the file pointer to a specific location using an offset and an origin, such as the beginning, current position, or end of the file. This is useful for random access, where you might need to jump to a specific part of a large file without reading through the entire contents. The ftel function returns the current position of the file pointer, which can be used to track progress or calculate file size. The rewind function resets the file pointer to the beginning, making it easier to reprocess the file from the start. These tools are essential for applications that require efficient navigation through large datasets, such as databases or media files. Error handling is a critical aspect of file I/O in C, as many operations can fail unexpectedly. The first step is to check if fopen returns null, which indicates that the file could not be opened due to reasons like incorrect permissions or a non-existent file. Once a file is open, you should monitor for errors using functions like fief to detect the end of the file, and fairer to identify any read or write errors. When an error occurs, it is important to handle it gracefully, such as by displaying an error message or attempting to recover. After handling an error, you can use clear to reset the error flags so that subsequent operations can proceed. By incorporating robust error handling, you can ensure that your programs remain stable and user-friendly even in the face of unexpected issues. Adhering to best practices for file I/O in C can significantly improve the reliability and efficiency of your programs. Always close files after you finish using them to release system resources and prevent data loss. For non-text data such as images or binary files, use binary mode to ensure that the data is stored and retrieved correctly. Validating input and output operations, such as checking the return values of functions, helps catch errors early and prevents undefined behavior. When working with text files, prefer fscanf and fprint for structured data, while using freed and fwrite for binary data to maintain compatibility and performance. These practices not only make your code more robust, but also make it easier to maintain and debug in the future. File I/O in C is a powerful tool that enables programs to store and retrieve data persistently, making it possible to handle tasks ranging from simple data saving to complex data processing. Text files are ideal for human-readable data, while binary files offer efficiency for machine processing. Mastering functions like fopen, freed, fwrite, and error handling techniques is essential for building reliable applications that can interact with external data sources. By understanding the nuances of file operations, you can create programs that are not only functional, but also scalable and maintainable. As you continue to explore C programming, practicing these concepts through hands-on projects will deepen your understanding and improve your ability to manage data effectively. Strings in C are arrays of characters that are terminated by a null character, which is represented as \0. This null character marks the end of the string and is essential for functions to know where the string concludes. Unlike other programming languages, C does not have a built-in string type, so strings are implemented as arrays of characters. These arrays are manipulated using functions from the string header file, which is included as string H. Efficient string handling is critical because improper management can lead to performance issues or security vulnerabilities, such as buffer overflows. Understanding how strings work at the low level helps in writing robust and secure code. Common string functions in C include strcpy, which copies the contents of one string to another, and strcat, which appends one string to the end of another. The strlen function returns the length of a string, excluding the null terminator. The strcmp function compares two strings lexicographically, returning a value that indicates whether the first string is less than, equal to, or greater than the second. These functions are part of the standard library and are widely used for string manipulation. However, it is important to note that some functions, like strcpy and strcat, do not check for buffer sizes, which can lead to security risks. Mastery of these functions is essential for effective string operations in C. The null terminator, which is a single character with a value of 0, is crucial for defining the end of a string in C. Without this character, functions that process strings may read beyond the allocated memory, leading to undefined behavior or security vulnerabilities. For example, if a string is not properly null terminated, a function like strlen might continue reading memory until it encounters a 0, which could be anywhere in the program's memory. This can cause crashes or unexpected results. Therefore, ensuring that all strings are correctly null terminated during their creation is a fundamental practice in C programming. Buffer overflow risks arise when functions like strcpy and strcat are used without checking the size of the destination buffer. These functions do not verify whether there is enough space to hold the data being copied, which can result in overwriting adjacent memory. This can corrupt data, cause program crashes, or even allow malicious code to execute. For instance, an attacker might exploit a buffer overflow to inject and run arbitrary code. To mitigate these risks, developers should use safer alternatives such as strncpy, which allows specifying the maximum number of characters to copy, or snprint, which limits the number of characters written to a buffer during formatted output. Safe string functions such as strncpy, strncat, and snprint provide mechanisms to prevent buffer overflows. The strncpy function copies up to a specified number of characters from the source to the destination, ensuring that the destination buffer is not exceeded. Similarly, strncat appends a specified number of characters from the source to the destination, maintaining the null terminator. The snprint function is particularly useful for formatted output, as it restricts the number of characters written to the buffer, thereby preventing overflows. These functions are essential for writing secure code, especially in applications where input validation is critical. Efficient string manipulation in C involves avoiding redundant operations such as multiple copies or concatenations. For example, repeatedly using strcpy or strcat in a loop can degrade performance. Instead, using pointers to traverse strings can be faster than indexing, as pointers allow direct access to memory locations. Additionally, pre-allocating sufficient memory for strings reduces the need for reallocation during operations, which can improve efficiency. By optimizing these aspects, developers can create more performant and maintainable code. String literals, such as hello, are stored in read-only memory and cannot be modified. Attempting to alter a string literal results in undefined behavior, which can lead to crashes or security issues. In contrast, character arrays like char str equals hello are stored in modifiable memory and can be altered as needed. It is important to distinguish between these two types to avoid errors. For example, modifying a string literal like char s equals hello, s0 equals h is unsafe and should be avoided. Always use arrays when modifications are required. Performance considerations in string handling involve minimizing unnecessary copies and using efficient techniques. For example, using pointers to traverse strings instead of indexing can improve speed. Additionally, caching the result of strlen in loops can prevent repeated calculations, which is especially beneficial for large strings. When working with binary data, the memcp function is preferred over strcpy, as it does not rely on null terminators. Understanding these nuances helps in optimizing string operations for both speed and memory usage. Best practices for string handling include validating input lengths before copying to ensure that the destination buffer is large enough. Initializing strings to empty by setting their first character to the null terminator prevents garbage data from being processed. Tools such as static analysis can also be used to detect potential issues like buffer overflows or uninitialized strings. By following these practices, developers can significantly reduce the risk of errors and enhance the reliability of their code. Efficient string handling in C requires a deep understanding of the language's low-level mechanics, such as null termination and memory management. Prioritizing the use of safer functions like strncpy and snprint helps prevent common vulnerabilities. Adhering to best practices, such as validating input and using static analysis tools, ensures that code is both secure and robust. By combining these approaches, developers can create high-quality C programs that are efficient, reliable, and resistant to common pitfalls. When writing code in the C programming language, maintaining a clear and consistent structure is essential for readability and collaboration. Always use indentation to visually separate blocks of code, whether it's 4 spaces or tabs, but be consistent throughout the project. Functions should be short and focused, ideally performing a single task to improve modularity and ease of debugging. For example, a function that calculates the sum of two numbers should not also handle input validation. Choosing meaningful names for variables and functions, such as calculate total price instead of calc, makes the code self-explanatory. Comments should be used to clarify complex logic or non-obvious decisions, but avoid over-commenting simple lines. Finally, keep code blocks from becoming too deep or lengthy, as this can make the program harder to follow and maintain. Proper variable and data type usage is fundamental to writing reliable C programs. Declare variables as close to their point of use as possible, which reduces the risk of errors and improves code clarity. For instance, instead of declaring all variables at the start of a function, initialize them when needed. Choose the correct data type for each variable, such as int for whole numbers, char for single characters, or float for decimal values, to ensure efficient memory usage and avoid type-related bugs. Always initialize variables explicitly to prevent undefined behavior, which can lead to unpredictable results. Global variables should be avoided unless absolutely necessary, as they can make the code harder to trace and debug. When a value should remain constant, use the const keyword to enforce immutability, which also helps the compiler optimize the code. Error handling is a critical aspect of writing robust C programs. Always check the return values of functions that can fail, such as malloc for memory allocation or fopen for file operations. For example, if malloc returns a null pointer, the program must handle this gracefully instead of crashing. Provide meaningful error messages to users or logs so issues can be diagnosed quickly. When system calls fail, use the error variable to determine the specific error and pair it with pairer to print descriptive messages. Never ignore invalid inputs or unexpected conditions, as this can lead to security vulnerabilities or crashes. During development, use assert to verify assumptions, but remember to remove or disable these checks in production builds, as they can impact performance. Memory management in C requires careful attention to avoid leaks and other issues. Every call to malloc, calloc, or realloc must be matched with a corresponding free to release the allocated memory. Failing to do so can result in memory leaks, where the program consumes more memory over time, potentially leading to crashes. Track all allocations, especially in complex programs, to to ensure they are properly freed. Tools like Valgrind are invaluable for detecting memory leaks and other issues during testing. After freeing a pointer, set it to null to prevent dangling pointers, which reference memory that has already been released. Dangling pointers can cause segmentation faults or undefined behavior, so always invalidate them after use. Documentation is key to making your code understandable and maintainable by others. Write comments to explain complex algorithms, edge cases, or non-intuitive decisions, but avoid redundant comments that merely restate the code. For public functions or APIs, use Doxygen-style comments to generate structured documentation, specifying parameters, return values, and potential errors. For example, a function that reads from a file might include a comment explaining what happens if the file is not found. Keep documentation up to date as the code evolves, as outdated comments can mislead developers. Well-documented code not only aids others, but also helps you remember the purpose of your own work during future maintenance. Testing and debugging are essential to ensure your C programs work correctly under all conditions. Write unit tests for critical functions to verify their behavior with different inputs, such as edge cases or invalid data. For example, test a function that divides numbers by checking what happens when the denominator is 0. Use print statements or debuggers like GDB to inspect variables and program flow during execution. Enable compiler warnings with flags like wall and Wextra to catch potential issues early, such as unused variables or type mismatches. Static analysis tools like ClangTidy can further identify code smells or security vulnerabilities. By combining these practices, you can catch bugs before they become problematic in production. In conclusion, adopting good habits in C programming leads to cleaner, more reliable, and maintainable code. Follow consistent coding standards to make your work easier to read and collaborate on. Prioritize error handling and memory safety, as these are common sources of bugs and crashes. Document your code thoroughly to improve clarity for others and yourself. Test your programs rigorously, including edge cases, to ensure they behave as expected. Finally, practice these principles regularly to build the discipline needed to write robust and efficient C programs. Over time, these habits will become second nature, making you a more effective and confident developer. Code optimization is a critical aspect of writing efficient and effective C programs. It involves improving the performance of your code by reducing execution time, minimizing memory usage, and making the program run more smoothly. However, it's important to remember that optimization isn't just about making the code faster. It also requires balancing readability and maintainability. A highly optimized piece of code that is difficult to understand can become a maintenance nightmare. Therefore, the goal is to find the right equilibrium between speed and clarity. Additionally, focus on the parts of the code that have the most significant impact on performance. For example, optimizing a small section of code that is executed millions of times can yield far greater benefits than tweaking a rarely used function. Always prioritize the critical paths in your program to ensure that your efforts lead to meaningful improvements. When it comes to algorithm efficiency, the choice of algorithm can have a profound effect on your program's performance. For instance, an algorithm with a time complexity of O of n log n is generally far more efficient than one with O of n squared, especially as the input size grows. This is because the former scales more gracefully with larger data sets. To achieve this, avoid unnecessary nested loops and redundant operations. For example, a loop that runs inside another loop can quickly escalate the time complexity. So it's essential to identify and eliminate such structures where possible. Additionally, focus on the overall time complexity of your algorithms rather than making minor tweaks to individual lines of code. A single change that reduces the time complexity of an algorithm can have a far greater impact on performance than 1,000 small optimizations. Loop optimization is a powerful technique for improving the efficiency of your code. One key strategy is to minimize the number of operations performed inside a loop. For example, if you have a constant value that is calculated repeatedly within a loop, pre-compute it outside the loop to avoid redundant calculations. Another approach is loop unrolling, which reduces the overhead of loop control by executing multiple iterations of the loop in a single iteration. This can decrease the number of branch instructions and improve cache performance. Additionally, avoid recomputing loop conditions repeatedly. Instead, store the loop condition in a local variable if it is used multiple times. This small change can save processing time, especially in loops that run a large number of times. Selecting the right data structure is fundamental to achieving optimal performance in C arrays, are particularly useful for contiguous memory access, which can improve cache locality and reduce memory latency. When traversing data, pointers often provide faster access compared to using indices, as they directly reference memory locations. However, be cautious with structs that have padding. Padding occurs when the compiler adds extra bytes between struct members to align data for the CPU, which can increase memory usage. To avoid this, consider using packed structs or reordering struct members to minimize wasted space. Choosing the appropriate data structure not only enhances performance, but also makes your code more efficient and easier to manage. Memory management is a crucial area for optimization, particularly in C, where manual control of memory is required. Dynamic memory allocation, such as using malloc or calloc, can introduce overhead and fragmentation. Whenever possible, use static arrays or pre-allocated memory to reduce the cost of allocation and deallocation. Reusing variables instead of declaring new ones can also help minimize memory usage and improve performance. For example, instead of declaring a new variable for each calculation, reuse an existing one if it is no longer needed. Finally, always ensure that unused memory is freed to prevent memory leaks. This is especially important in long-running applications where memory leaks can accumulate over time and degrade performance. Compiler optimization flags can significantly enhance the performance of your C programs. By enabling flags such as O2 or O3, you allow the compiler to automatically apply a range of optimizations, including inlining functions, removing redundant code, and reordering instructions. The march equals native flag tells the compiler to optimize for the specific CPU architecture, which can unlock additional performance gains by utilizing advanced instruction sets. However, avoid using O0, which disables all optimizations and is typically used for debugging. While O0 can help with debugging, it is not suitable for production code, as it results in slower and less efficient executables. Understanding these flags and their trade-offs is essential for achieving the best possible performance. Inline functions are a useful tool for reducing the overhead of function calls, especially for small, frequently called functions. By By marking a function as inline, you instruct the compiler to replace the function call with the actual code, which can eliminate the cost of pushing and popping the stack. However, overusing inline functions can lead to code bloat, as the same code is duplicated in multiple places. This can increase the size of the executable and potentially reduce cache efficiency. To strike the right balance, use inline functions judiciously and consider compiler-specific hints, such as attribute novice inline, to enforce inlining where it is most beneficial. Always evaluate the trade-offs between performance and code size when deciding to use inline functions. Avoiding redundant calculations is a simple yet effective way to improve code efficiency. For example, if a calculation is repeated multiple times within a loop, store the result in a variable instead of recalculating it each time. This reduces the computational load and can lead to significant performance gains. Similarly, use constants for values that do not change, such as mathematical constants like pi or the speed of light. Declaring these as const variables ensures that their values are computed once and reused throughout the program. Additionally, pre-compute values that do not change during the execution of the program, such as loop bounds or fixed parameters. These small optimizations can add up to substantial improvements in performance, especially in computationally intensive applications. Profiling and benchmarking are essential steps in identifying and addressing performance bottlenecks in your code. Tools like gprof and valgrind can help you analyze the execution of your program and pinpoint which functions or sections of code are consuming the most resources. By focusing on these hotspots, you can prioritize your optimization efforts where they will have the most significant impact. For example, if a particular function is called millions of times, even a small improvement in its execution time can lead to a noticeable overall gain. Always compare the performance of your code before and after making changes to ensure that your optimizations are effective. This iterative approach helps you avoid wasting time on unnecessary tweaks and ensures that your efforts are directed toward meaningful improvements. Optimization is not a one-size-fits-all solution. It requires a deep understanding of the trade-offs between performance, readability, and maintainability. While it is tempting to pursue the fastest possible code, it is equally important to ensure that your code remains easy to understand and modify. A well-optimized program that is difficult to maintain can become a liability in the long run. Therefore, prioritize readability and maintainability as much as performance. Finally, combine multiple optimization strategies to achieve sustainable performance gains. For example, using efficient algorithms, optimizing loops, and leveraging compiler flags can work together to create a highly efficient program. Remember that optimization is an ongoing process, and continuous profiling and refinement are key to achieving the best results. C is a procedural language, but can mimic object-oriented programming concepts through clever use of structures and function pointers. The 4 key principles of object-oriented programming are encapsulation, abstraction, inheritance, and polymorphism. This session will explore how to implement each of these concepts in the C programming language. By understanding these techniques, you will be able to write more organized and modular code, even in a language that was not designed with object-oriented programming in mind. Encapsulation in C can be achieved by using structures to bundle data and functions together. While C does not have classes, you can simulate methods by storing function pointers within a structure. For example, a structure might contain data fields such as a name and a value, along with function pointers that perform operations on that data. This approach allows you to group related data and behavior, making your code easier to manage and understand. Abstraction in C involves hiding implementation details and providing a clean public interface for interaction. This can be done by creating functions that handle complex operations behind the scenes. For instance, a library structure might have open and close functions that manage internal resources without exposing those details to the user. This separation of concerns makes your code more flexible and reduces dependencies between different parts of your program. To simulate inheritance in C, you can use struct composition by embedding a base structure within a derived structure. This allows the derived structure to reuse the data and functions of the base structure. For example, a circle structure might include a shape structure as a member, inheriting its properties and methods. This technique enables code reuse and creates a hierarchical relationship between structures, even though C does not support traditional inheritance. Polymorphism in C can be implemented using function pointers stored within structures. By defining a function pointer in a base structure, you can allow different derived structures to override its behavior. For example, a shape structure might have a draw function pointer that points to different implementations for circles and squares. This dynamic behavior enables you to write generic code that works with multiple types, providing flexibility and extensibility. Let us look at a practical example of object-oriented programming. In C, we can define a vehicle structure with function pointers for start and stop operations. A car structure and a bike structure can then be created, each implementing their own start logic. By using a vehicle pointer to call the start function, we demonstrate runtime polymorphism. This approach allows us to treat different vehicle types uniformly while maintaining their unique behaviors. While C can simulate object-oriented programming concepts, there are limitations to consider. The language lacks built-in features like classes or inheritance, requiring manual management of function pointers and structures. This can increase the complexity of your code and introduce potential errors if not handled carefully. However, the trade-off between flexibility and complexity can be worthwhile when building large or modular systems. In conclusion, C can effectively simulate object-oriented programming concepts using structures and function pointers. Encapsulation, abstraction, inheritance, and polymorphism are all achievable through careful design and implementation. By practicing with real-world examples, you will gain the skills needed to write more maintainable and scalable C programs. These techniques will help you leverage the strengths of C while adopting the benefits of object-oriented programming. Threads are the building blocks of concurrent execution within a single program. They allow different parts of a program to run simultaneously, sharing the same memory space and resources. This makes them more efficient than full processes, which require separate memory allocations. Concurrency, the ability to execute multiple threads at the same time, is a powerful tool for improving performance, especially in applications that handle multiple tasks like input-output operations, data processing, or network communication. In the C programming language, the POSIX threads library, commonly known as pthreads, provides the necessary functions to create, manage, and synchronize threads. However, while threads can enhance performance, they also introduce challenges. Without proper synchronization mechanisms, threads may interfere with each other, when accessing shared data, leading to unpredictable behavior. This is why understanding and implementing synchronization techniques is essential for reliable concurrent programming. To create a new thread in C, we use the pthread create function. The syntax for this function is straightforward, but requires attention to detail. The first argument is a pointer to a thread identifier, which allows the program to reference the newly created thread. The second argument is a pointer to a thread attributes object, which can be set to null for default settings. The third argument is the function that the thread will execute, and the fourth argument is a parameter passed to that function. For example, a thread can be tasked with handling input-output operations, while the main thread continues processing data. This separation of tasks allows the program to remain responsive and efficient. It is important to note that once a thread is created, it runs independently, but all threads within a program share the same address space. This shared memory is both a benefit and a potential source of errors, which is why careful management is required. When multiple threads access shared resources, such as variables or data structures, they must do so in a controlled manner to prevent conflicts. This is where synchronization mechanisms like mutexes come into play. A mutex, short for mutual exclusion, ensures that only one thread can access a resource at a time. The pthread mutex lock function is used to acquire a lock, and pthread mutex unlock is used to release it. These functions are essential for protecting critical sections of code where shared data is accessed. Another important synchronization tool is the condition variable, which allows threads to wait for specific conditions to be met before proceeding. Functions like pthreadCanWait and pthreadCanSignal enable threads to communicate and coordinate their actions. Without these mechanisms, race conditions can occur, where the outcome of a program depends on the unpredictable order of thread execution. This can lead to data corruption, incorrect results, or even program crashes. Concurrency introduces several common challenges that programmers must be aware of. One of the most critical is deadlock, a situation where two or more threads are waiting for each other to release resources, resulting in a permanent standstill. For example, if thread A holds a resource and waits for a resource held by thread B, while thread B is waiting for the resource held by thread A, neither can proceed. Another issue is starvation, where a thread is unable to gain access to a resource because other threads are constantly using it. This can happen if resource allocation policies favor certain threads over others. Data corruption is another risk, as unguarded access to shared data can lead to inconsistent or incorrect values. Finally, debugging concurrency issues is notoriously difficult due to the non-deterministic nature of thread execution. The same code can behave differently each time it runs, making it hard to reproduce and fix problems. To illustrate these concepts, let's consider an example where a thread increments a global variable while protecting it with a mutex. The main thread initializes the variable and creates a second thread to perform the increment. The mutex ensures that only one thread can access the variable at a time, preventing race conditions. This simple example highlights the importance of proper synchronization. However, writing robust concurrent code requires more than just using locks. Best practices include minimizing the amount of shared data, as reducing dependencies between threads decreases the likelihood of conflicts. Consistently using locks whenever accessing shared resources is crucial.